Artificial intelligence, or AI, has been a dream for centuries. From ancient myths of automatons to modern science fiction, the idea of creating machines that can think has always fascinated us. The term artificial intelligence was first coined in 1956 at the Dartmouth Conference. This marked the birth of AI as an academic discipline. Early pioneers like Alan Turing posed the question, can machines even think? Turing proposed a test, now known as the Turing test, to determine if a machine can exhibit intelligent behavior, indistinguishable from a human. He also introduced the concept of a universal machine, which is a theoretical construct that can actually simulate any Turing machine. This idea laid the foundation for modern computers. Now, AI isn't just about mimicking human behavior. At its core, it's mathematical. For instance, consider the simple equation y equals mx plus b. Now in AI, we often try to find the best m and b to fit our data. This is the basic form of learning from data. Now, let's dive into the distinctions. AI is a broad field aimed to create machines that can perform tasks requiring human-like intelligence. This includes problem solving, understanding language, and even perception. Meanwhile, machine learning, or ML, is a subset of AI. It's actually about teaching machines how to learn from the data instead of being explicitly programmed. An ML algorithm can use data to make predictions or decisions. Think of it as fitting a line to a set of data points, but on a much larger scale. Now, deep learning is a subset of ML. It's inspired by the structure of the human brain, using algorithms called neural networks. Now, these networks have many layers, hence deep. Each layer transforms the data, helping the machine recognize complex patterns. Now, imagine a neural network as a multi-layer sandwich. The bread slices are the input and the output, and the fillings are the middle and hidden layers. Data enters from one side and gets transformed as it moves through the layers. In fact, by adjusting the weights in these layers, the network learns. From voice assistants to self-driving cars, the advancements in AI, ML, and deep learning are shaping our future. These technologies, rooted in mathematics and decades of research, are bridging the gap between machine and human intelligence. As we stand on the brink of an AI revolution, it is essential to understand its history and the intricate layers that make up this fascinating field. The journey of AI, from a dream to reality, is a testament to human ingenuity and perseverance. Thank you so much for watching this video. Now remember, this is just video 1 out of 20. By the time you finish this series, you'll have learned the basics of machine learning and computer vision. Hi everybody, this is video 2 out of 20 in our beginner series on Introduction to AI. Let's dive into 4 use cases of AI today: healthcare, education, transportation, and environmental science. Let's first consider healthcare. Now, in the realm of medicine, AI has become the silent sentinel, the guardian angel that never sleeps. Machine learning algorithms sift through vast amounts of data, predicting disease outbreaks, personalizing treatments, and even assisting in complex surgeries. Even back in 2018, researchers out of King's College London were able to significantly improve a process known as segmentation accuracy, assisting medics and researchers to more rapidly and quickly identify brain tumors. Now let's jump over to education. AI-driven educational platforms offer personalized learning experiences, adapting to each student's pace and style. The barriers of traditional education crumble, and knowledge becomes a universal treasure accessible to all. For example, the MIT Media Lab's Personal Robots group has developed an AI-powered tutoring system called Teachable Machines. Now, teachable machines can analyze student interactions with a virtual robot to identify their learning progress. This system can then provide personalized feedback and recommendations to help students improve their skills. Let's now consider transportation. The age-old dream of Icarus was to fly. Now, while we may not have the wing of wax and feather today, we have something better: AI-driven autonomous vehicles. They promise safer roads, reduce traffic, and a world where every journey is a step into the future. Now, this element of safety is important, as demonstrated by Anthony Corso's publication in 2022 in the Journal of Artificial Intelligence, titled "A Survey of Algorithms for Black Box Safety Validation of Cyber-Physical Systems." The purpose of the paper was to quickly survey the state-of-the-art algorithms that allowed black box safety validation of cyber-physical systems that are essentially controlled by software but interact with the physical world. Now, the authors specifically used a method called Monte Carlo simulation to randomly generate inputs to the cyber-physical system and then simulate a system response, providing more rigorous approaches for testing before deployment. Now let's jump from the urban environment to the environment. AI-powered drones monitor deforestation, track endangered species, and optimize renewable energy resources. We are not just passive observers, we are stewards, guided by the wisdom of machines. Now, at the beginning of August 2023, a paper published out of the China Three Gorges University proposed a state-of-the-art renewable energy forecasting system meant to help society with daily planning and power system instability. In their work, they propose a novel transformer-based model named the Graph Patch Information. Their method uses segment-wise self-attention, an adaptive adjacent matrix, and even a new training strategy that uses both self-supervised pre-training followed by fine-tuning. The tapestry of our future is woven with the threads of code and algorithms. As we embrace the magic of AI, we must remember our role, to wield this power responsibly, and to ensure that the future that we create is one of hope, prosperity, and unity. This is video 2 out of 20 in our beginner's series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. This is video 3 out of 20 in our beginner's series and introduction to AI. Now, in the realm of human history, there have been tools, inventions, and ideas that have transformed our world. Today, we stand on the precipice of another revolution, artificial intelligence, or AI. Now, early AI researchers believed that the essence of intelligence could be distilled into mathematical formulas. They envisioned a world where machines could think by following precise, logical rules. But what is this mysterious force? How does it think, learn, and evolve? Let's embark on a journey to unravel the enigma of AI. At its core, AI is like a child. It learns from experience, but instead of human experiences, it learns from data. Imagine a vast library. Each book represents an algorithm, a set of instructions. AI uses these algorithms to process information, make decisions, and learn. One of the most powerful algorithms is the neural network. Much like our brain has neurons, these networks have nodes. They connect, they interact, and then they make decisions. At its heart, a neural network uses a simple equation. Output equals weight times input plus bias. Think of it as a balanced scale, adjusting weights to find the right balance. These weights and biases are tweaked over time, allowing the network to learn and to make better decisions. In fact, imagine walking into the grandest Starbucks of the digital realm, where multi-layer neural networks are the baristas, crafting the perfect brew every time. As you place your order, think of it as a raw data input. Now, the first barista or neural layer takes your basic order, say a latte. As your order moves down the counter, each barista adds a touch of magic. One adjusts the milk temperature, another adds the right amount of foam, and yet another might sprinkle some cinnamon on your PSL. By the time your cup reaches the end of the counter, it's been transformed into the perfect personalized latte, just the way you like it. And the secret recipe? The meticulous notes of weights and biases that each barista keeps, refining them with every cup they craft to ensure that your next visit is even more delightful. But here's the frothy twist. There's a special barista known as the activation function who decides how each ingredient is added. This barista ensures the balance is just right, not too strong or too mild, making sure that your coffee experience is consistently magical. And after you take that first sip, well, the feedback you give it is like the back propagation in the network, helping our barista team tweak their techniques for your next visit. So, the next time you think of a multi-layer neural network, imagine the bustling AI Starbucks that we just visited, where every cup is a blend of precision, art, and a dash of digital magic. Now, meet the Convolutional Neural Network, or CNN. It's like an artist specializing in images. It can recognize patterns, shapes, and objects, making it the backbone of image recognition. The core math? It's about applying filters to images. Now imagine placing a magnifying glass over a picture. focusing on a small part at a time. That's convolution. These filters help CNNs detect features, from simple edges to complex patterns, allowing it to see and thereby understand images. Now imagine that you're at a gallery staring at a giant intricate painting. Now envision a tiny robot artist with a magnifying glass, meticulously examining each section of artwork. This little artist sits at the heart of a convolutional neural network, or CNN. Instead of seeing the entire painting at once, the CNN artist actually focuses on tiny patches, identifying simple patterns like strokes, colors, and textures. It's like recognizing the individual brush strokes that make up a beautiful sunset or a delicate shading in a portrait. As our tiny artist moves deeper into the gallery or the layers of the CNN, it starts to piece together these simple patterns to recognize more complex features, maybe the curve of a smile or the silhouette of a mountain. By the time it reaches the final room, it can appreciate and understand the entire artwork, recognizing intricate scenes and subjects. So the next time that you hear about a CNN, think of our diligent robot artist using its magnifying glass to uncover the magic behind every pixel. Now let's jump to the recurrent neural network, or RNN. Picture it as a storyteller. It remembers past events, making it perfect for understanding sequences like music or language. Its magic lies in the loops. An RNN feeds its output back into itself. It's like reading a book and remembering the previous page to understand the current one. This looping structure allows it to remember and process sequences, making it adept at tasks like language translation. Now picture yourself at karaoke night, with a song playing that tells a story from the start to the finish. Now imagine a musical robot friend named RNN with an incredible memory, humming along. Unlike other robots, RNN just doesn't focus on the current note, it actually remembers the entire melody leading up to it. So each time a new note plays, RNN thinks, oh, this note follows that dramatic chord from earlier. It's like having a continuous echo of the song's history in its circuits, allowing it to anticipate the upcoming chorus or bridge. As the song progresses, RNN adjusts its humming based on the notes it remembers, ensuring it's always in tune with the story's flow. It's this magical memory loop that lets RNN excel at whatever task it is given, like understanding song lyrics or predicting the next word in a sentence. So, the next time you think of a recurrent neural network, envision our musical robot RNN echoing the past and harmonizing with the present, all while eagerly awaiting the next note in the sequence. The Transformer is not just a toy, but an AI marvel. It revolutionized language understanding. It's sort of like a wise sage, understanding context and relationships in data. Now what's its secret? Truly, it is the attention mechanism. Imagine listening to a crowd but focusing only on the most important voices. That's how the Transformer prioritizes information. They weigh the importance of different pieces of data, ensuring that the most relevant bits get the attention that they deserve. And the CLIP algorithm? Well, think of it as a bridge. It connects words to images, understanding and generating descriptions. It's the poet of the AI world. CLIP's genius is its ability to compare. It looks at an image and a description, and then it measures how well they match. It's like pairing the right caption on a photo in a gallery. By understanding both the text and the images, CLIP can make connections that other algorithms just might miss. Picture this, a magical chest filled with countless images and words, and every time that you pull out a picture, a perfect description magically appears. That's the enchantment of the CLIP algorithm. But what's the spell behind it? Dive into the world of vectors. Now in the realm of CLIP, every image is actually transformed into a special kind of magical dust called a vector. Now these vectors, much like the coordinates on a treasure map, have a unique position in the vector space. The closer two vectors are, the more similar the images and the word. Now here's the real sorcery and where it happens. CLIP uses a magical scale called the dot product to measure how well an image and a description match. Imagine two vectors dancing towards each other. If they groove and are in harmony, then the dot product is high, signaling a near perfect match. But if their dance is even a little bit out of sync, then the dot product is probably low. By comparing these dance scores for various word-image pairs, CLIP can then pick the most enchanting match. So the next time you marvel at how CLIP conjures the perfect caption by an image, remember this mesmerizing dance of vectors behind the scenes. Now, these concepts might seem complex, but remember, every expert was once a beginner. The world of AI is vast, but it's built on simple principles. Imagine stepping into a vibrant realm where numbers, symbols, and data dance together to create enchanting AI wonders. In this world, linear algebra is the spellbook, with vectors and matrices weaving together to form the backbone of neural networks. These magical grids of numbers transform and shapeshift, guiding AI on its quests. Meanwhile, the thrilling adventures of calculus let AI scale mountains and valleys, seeking the best paths. With guidance of differential calculus and gradients, AI can then fine-tune its strategies, ensuring that it's always on the right track. Now, entering the bustling marketplace of probability and statistics, where AI fortune tellers can predict the future. Here, using tools like Bayes' theorem and statistical distributions, they can gaze into crystal balls or datasets to make informed decisions. But that's not all. In the grand arena, AI champions battle challenges using optimization. With their trusty sidekicks, loss functions, and gradient descent, they refine their skills, striving for perfection in every task. But the adventure doesn't end there. In the vast libraries of the realm, scholars of information theory are still unlocking the secrets with keys like entropy, while explorers chart new territories using graph theory, finding the best routes and connections. And for those who love unraveling mysteries, differential equations and complexity theory offer puzzles and riddles, helping AI understand the rhythms of change and the intricacies of algorithms. You will learn across the rest of these 20 videos how a subset of these concepts will be put to the test on your journey to learning AI. You, yes you, have the power to understand and harness this technology. It's not just for the tech-savvy or the mathematicians. AI is for the dreamers, for the thinkers, and the believers. This is video 3 out of 20 in our beginner series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. This is video 4 out of 20 in our beginner series and introduction to AI. Imagine stepping into the watch floor of a futuristic spaceship, ready to explore the vast universe of artificial intelligence. That's what diving into Jupyter Lab feels like. Jupyter Lab isn't just an IDE, it's your personal spacecraft, designed to make your journey into the world of Python and AI both thrilling and intuitive. With its sleek interface and powerful tools, you'll feel like a space captain, navigating through galaxies of code, creating stellar programs, and watching your AI dreams come to life. As budding AI engineers, you'll start by mastering the basics. You'll learn how to launch your very own Jupyter Notebook, a magical canvas where you can write, test, and even see your Python code in action. It's sort of like having a conversation with your computer. Want to see the result of a calculation, visualize data, or even display a cool graphic right away? Just hit run and watch the magic unfold right before your eyes. And the best part? Mistakes are just wormholes to new discoveries. With Jupyter Lab's user-friendly interface, debugging becomes like a fun puzzle, guiding you closer to your AI aspirations. But the journey doesn't stop there. As you become more familiar with this cosmic tool, you'll also discover its endless possibilities, from importing powerful Python libraries to harnessing the might of machine learning algorithms. Jupyter Lab is the launch pad for all of your AI adventures. So strap in, future AI engineers. With Jupyter Lab as your co-pilot, you're in for an exhilarating ride through the cosmos of code. Alright, so now that I've introduced you to Jupyter Lab, let's walk through some specific steps that will actually teach you guys how to set this up on your own computer. Now for this tutorial, we're going to walk through how to do it using Apple iOS. I'm using the iOS operating system. So the first thing that I want to highlight is that if you want to actually set up Jupyter Lab on a Mac, either with Intel or Apple Silicon, it's pretty straightforward. But I would strongly recommend that we use a tool like Homebrew. Now, Homebrew is a package manager for Mac OS X, also Linux, that actually makes it easy to install software. And if you haven't installed Homebrew yet, this is exactly how you do it. So you want to actually first go into your search bar. You want to look for Terminal. And from Terminal, you can then open up this window, which I have up on my side. For some of you, it might be very small, and so the way that you increase the font is actually just click on Command and then plus, 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 until you get to the size that is amenable for you. So the first step is to basically take this Install Homebrew section and then copy and paste. Before we jump into it, let me just tell you why you want to use a package manager. So Package Manager actually is a tool that helps you automate the process of installing, updating, and removing software packages. And the main reasons why you want to use it are, one, for simplicity, because this basically handles the whole process. Two, consistency, because a package manager will make sure that your software got installed correctly and consistently. Three, also for safety, because they usually use the source software from a trusted repository, which minimizes usually the risk of downloading malicious or bad software. And finally, it also provides you an opportunity for updates and maintenance that are easy. So if software has a security vulnerability, the package manager can quickly update that to a patched version. So with that, I'm just going to basically copy and paste this little homebrew blob, and you'll see me run it here. It's asking for sudo access, so what that means, I don't even remember my password, shoot. Let's try that again. That means superdo, or super user. So now it's just confirming, like, am I cool with that? I'm saying yes, yes. And now it's just sort of doing its thing. So while it looks for that software update, you should have a similar experience. And now it's basically downloading all those tools. You might want to remain on standby because usually a lot of this system will require, obviously, like a strong internet connection. So I wouldn't recommend doing this disconnected from the internet because it's actually downloading it from an internet repository. All right. Now that that's completed, you now should all have Homebrew in your home directory. So the next step is for us to actually install Python. Now, Apple Silicon Macs usually come with Python installed, but it's probably a good idea to just, install a separate version for development purposes. So we're going to try using Brew, which you just downloaded, to help you install Python. And this is to ensure compatibility. So I'm just going to type brew install Python. I actually already have it, but you'll notice that it's basically setting it up yet again, and we're generating some of these certificate bundles. And this is, again, another place where it might hang and take a little bit of a while. Oh, here we go. So it's just basically pulling all of those required, packages to help Python run. This is really exciting. Feel free to walk away. You'll usually get an indicator once this completes. All right, so you'll know it's done when you can basically type in the terminal again. Now what we're going to do is just check on the version of Python that we installed. Looks like I have Python 3.9.16. And now the final step is for us to finally, after these preliminary steps, install Jupyter Lab. So what I'm using is pip3 actually. 3 indicates Python 3, and pip is basically Python's package manager. So similar to how we have a package manager for your actual computer or your iOS, which is Brew, we now also use pip to manage Python packages. And Jupyter Lab, at the end of the day, is sort of wrapped up into this sort of Python package. So I'm typing pip3 install and Jupyter Lab. And for me, it's basically streaming requirements are already satisfied because I have been using this for pretty much most of my life. But for you guys on the call and on this video, you'll notice that it will probably ask for permissions to just make sure to provide those authorizations. And once you're ready, this is where the magic begins. You simply type in Jupyter, and space lab will actually open up a whole interface. If you do Jupyter Notebook, that will also open an interface, but we'll get there when we get there. So let's start with Jupyter Lab. And you'll see here that it's serving on my local host, and this is exactly what it will and should look like. So now you've pretty much opened up a new tab in your default browser with this Jupyter Lab interface. And it's from here that we can actually create new Jupyter notebooks, text files, or also open the terminal again. You might want to also know how to just shut down the Jupyter Lab. So what you want to do is actually go back to the terminal. And what I'm pressing right now is actually Command C. Just kidding. I'm actually pressing Control C. And then you'll see that it asks you if you want to shut down this Jupyter server. So I was too slow. I basically want to, again, click on Control C and quickly say yes, Y, and then enter. And that shuts down the node. And then you'll know it worked because as you saw right here, it then says the server connection error has popped up. It says that the connection could no longer be established. And that's about it. So excited to show you guys how to move forward in the next video. And in this video, you've actually learned how to successfully set up Jupyter Lab on your Mac with Apple Silicon. This is video 4 out of 20 in our beginner series, An Introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. All right, guys, hello. Welcome to the world of Python, a powerful language that is at the heart of many artificial intelligence applications. So today, we're going to cover foundational concepts that you'll need to kickstart your AI journey with Python. This is video 5 out of 20 in our beginner series, An Introduction to AI. So first, if you remember, I wanted us to pull up Jupyter Notebook. And so in our last video, we walked through Jupyter. This time, what I'm going to do is actually just type Jupyter Notebook. And you'll see that in your browser, as you're seeing on the right side, this is popping up. Now, what I want you to do here is just click on New, and then click on Python 3 to identify that as your desired kernel. And from here, we'll actually start typing. Now, I'm just going to call this video 5 because this is the 5th in our series. You can name it whatever you want. And what I'd like to do is actually walk through some of these principles by actually showing you code blocks. So the first that we're going to visit is called variables and data types. Now in Python, you can think of a variable like a container that stores data. So you can think of it as a labeled box where you can actually put things inside. So it's going to be super straightforward. I'm going to say name equals, and then open quote, Sean, end quote. I'm going to type age equals 900 because I'm obviously an elf or robot or cyborg. And am I a student? Well, I'm a student of life, so I'm going to say is student is equal to true. Now, when I click Command Enter at the same time, this stores these variables. So when I open the cell, you can then see that if I typed a name and ran it, it would say Sean. And if I wrote type outside of name, it would tell me that it's an str. And what is that? Well, that tells us that the name variable is actually storing a string data type. And you might be wondering, what is a string? High level, a string is essentially a series of different chars or characters. And so when you have many characters strung together, LOL, it is a string. And strings are typically how we represent a lot of textual data, like my name, for example. Now, if you remember what I was saying about age, I said that my age was 900. But how does the machine think of that data point? So I'm going to go run the function type, which is, again, a function that's native to Python 3. I'm going to say, what is the type of the variable age? This time it's saying that it saved it as an integer data type. Integers are one way of basically storing numbers. Basically, they are full representations of a number that are not included in something known as a float. So most numbers are either represented as either a float or an int. If I changed age to 900.0, which is weird because ages normally aren't represented like that, then it would change the type of the age to a float value. So for simplicity's sake, we're just going to keep them as integers for now. And we'll finally just interrogate the final value here, which is student. And you'll see here that stands for Boolean. So this is telling me that the type of a response like capital T, lowercase r-u-e, true, is a Boolean representation, which basically is a truth value. There's only two values here. It can either be true or false. And both of those are stored as a variable type known as Boolean. So now that we have that under our belt, I'm going to jump next to basic operations. And when I say basic operations, we're going to basically go through some basics of arithmetic. So let's say that our result is 10 plus 10. The main point that I want you to know here is that Python can actually do basic math. Here, 10 plus 10 equals 20, so it can definitely add. 10 minus 10 is 0. It can also subtract. 10 star 10 is 100, so it can also multiply. And finally, 10 divided by 10 will return 1.0. And that is basically the core of these different types of arithmetic functions. You can add, subtract, multiply, and even divide using Python. Next, we're going to jump into something known as control structures. And here I'm going to just teach you the high-level concept of if-else. Now, control structures allow you to make decisions in your code. And the if-else statement is honestly a really fundamental decision-making tool. So I'm going to say temp underscore F for temperature in Fahrenheit, and I'm going to call it 80. We're going to make a little temperature thermostat here. I'm basically going to say if the temperature in Fahrenheit is greater than 80, I want to print it is so hot. Whoops, typo. There we go. It is so hot. Now, if the temperature is less, or if the temp F is less than, let's say 50 degrees, then you would print it's cold outside. Again, let's assume, of course, that I'm going off rough East Coast standards. I know some people in the Midwest in the US would think that around 50 and less than 50 is still pretty brisk. And for any other condition else, let's print the weather is perfect. So you'll see here that when I set temp F to 80, since we actually didn't exceed 80, the weather is still perfect. But if I go up to, say, 81, even one value higher, now I've hit my threshold, and this control statement thinks it is so hot. And so in the context of AI, decision-making is super crucial. And for instance, here, the AI thermostat uses this type of logic to decide whether or not it is identifying the environment as hot or cold. Now that you've got this concept, let's jump to the next chunk, which is about loops. Now, loops allow you to repeat a block of code multiple times. This is especially useful in AI when you're trying to process large data sets. So first, let's go through a for loop. So I'm going to say, I'll make a for loop, and I'll call it fruit, a bunch of fruits. And let's just store in our fruit list. We'll do kiwi. Just came back from Hawaii. Let's do papaya. And let's definitely do mango. So for fruit, in fruits, print fruit. And when I run this code, it will just basically print them all out. And that's an example of going through a for loop, and it terminated once we hit the end of the list. Now, let's visit a while loop, which is a little bit similar, but the difference with while loops is that it will repeat the action until a condition the user defines is met. So in a while loop, let's set a counter, and I'll start my counter at 0. I'm going to basically set the condition. So while my counter is less than, I don't know, I like the number 7 because it's a prime number. While the counter is less than 7, I want to print the counter value. And in order to change the conditions, otherwise it would stay at that value forever, let's increment by 1 until we hit 7. And so I'm now going to run this. And that failed because I called it count, not counter. Debugging, guys. And let's run that. So you'll see that we begin at 0, and then we basically continue printing those values and incrementing. And once we hit a value that was indeed equal to 7, the entire while loop stopped. And so in general, in AI, loops could be used to iterate through data points and adjust model parameters, or even train a model over multiple epochs. We'll get to that later, but for now, these are sort of the core fundamental principles within the Python language that you should know. So, congratulations. You have taken your first steps into Python programming in the context of AI. And now with these foundational concepts, you are well on your way to diving deeper into the more advanced topics like functions, libraries, and eventually building your own AI models. All right, this is video 5 out of 20 in our beginner series and introduction to AI. By the end of this series, you will be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Now, I also want you all to remember that indeed, the key to mastering Python is practice, just like learning any other language. If you don't use it, you lose it. So, experiment with the code snippets, modify them, and see the results. Happy coding! Hello, AI enthusiasts. Today, we're diving into the magical world of Python functions and modules. This is video 6 out of 20 in the beginner's series and introduction to AI. Now think of functions as your personal gremlins doing tasks for you, and modules as the vortex filled with these pre-made gremlins. So first, we're going to go through the concept of defining and calling functions. So imagine that you actually have a repetitive task, like let's say you have to greet so many people. Now instead of writing the same code again, you can actually create a function to greet them. So let's just sort of jump into it. So I've already opened up in my Jupyter lab a little code notebook, and we're going to call this definition summon name. I'm actually going to use summoning because we were talking about gremlins, and for those of you who are into that, it is a throwback to something from the late 80s, early 90s. So what I'm typing here is a little greeting. Star Bunny, by the way, for those of you who are paying attention, is actually a reference to this shirt, this little half star cloud, half rabbit that I built at the beginning of the year. And so you'll see here it says hello gremlin, and then we can actually call the function here. And so I would print summon, and then you'd input that name variable. And so in this case, let's use my name, Sean. So when I run this, it says, hello gremlin Sean, are you ready to dive into Star Bunny's course on AI? Now here, summon is our function or gremlin, and name is the information that we gave that function to work with. You'll also notice that I did a little weird thing here where there's this sort of curly bracket that has name. This is basically a way to pass in your function, basically put the user input into the string and embed it. In order for that to work, you also have to remember this little F flag here in the string. So just want to make sure that you guys are tracking that. So now that we know this, let's jump to the next segment of this conversation. So we've already done our script here, and now I want to teach you guys what it means to actually import a full-on module. So now we're going to work with NumPy. Now, high level, let's jump back to the concept of modules. Modules are like toolkits. For AI, we often use the NumPy toolkit for mathematical operations. So I can type import numpy as np, and I run that, and for me it works. If you didn't have this working, make sure to go back to your terminal and type pip3 install and then numpy. Now, of course, for me, this requirement was already satisfied, but if you got an error, it's probably because you just didn't have this. And now that we did this, I'm going to tell you that we should create an array of numbers, and this is how you do it. Numbers equals np, which is our shortcut for NumPy, and then I would call a function known as array. And then in array, all functions have sort of this open and close soft curly bracket. And then in that, I would then do a hard bracket, which denotes a list. And here I'm going to basically build my array of a bunch of even numbers. And then I'm going to actually try to calculate the average by invoking, again from the NumPy library, the mean function. And then I'm going to pass the variable that I just wrote up there. And then here I'll print, and then we'll do f. The average is, and then average. Now you'll notice that this is one of my favorite sort of constructions because it allows me to take variables passed in the block and actually have it inserted into the string output. Also, notice how we used NP as a nickname for NumPy. This is purely to make your life easier. You can actually name it whatever you want, but a common construction is calling NumPy NP. Now let's jump into Pandas. So importing libraries with Pandas is a really common pattern, again in CV and in ML, because Pandas is sort of like a super smart librarian, and it helps us essentially organize and analyze our data. So let's look at import Pandas as PD. I'm doing a little shortcut again. And this time I'm going to create a little data set. So data equals, and then I'm going to do open bracket. And then what I'm doing here is actually creating two data fields. So names, and bear with me, this is sort of just the structure that you would use. I'm watching the Foundation series, so I'm going to put Demerzel, one of my favorite characters. She is a mystery character. I will not spoil it, but I will leave some hints here, which is that when I want to make a sort of database of our ages, my age, if you remember from the last video, I said I was 900. We'll say Demerzel is 13,000 years old, and my friend Nick is 31. And after that, what I want to do is actually convert this data into data frame. So we'll call it df for data frame, and then I'm going to call the pandas library, call the data frame function, and then bind the data variable I just wrote above into that data frame. And then we're going to print that data frame. And let's see what it looks like. So here it's sort of thinking, and this is the output. And you'll see that now we have a neat table with names and ages. Here you can imagine that there is great power when we are dealing with massive data sets using, again, pandas. Finally, last but not least, I'm going to teach you how to work with NLP and specifically with Hugging Face. But of course, the goal of this video is just to understand the concept of, again, calling different types of Python modules and then the functions within them. So first, I want to make sure that you actually have the necessary library. So make sure you go into your terminal and type pip install transformers. Again, as you'll see for me, this requirement was already satisfied because I work with this pretty regularly for work. But now that I actually have my code block, what I'm going to do is pull from Hugging Face. Ironically, transformers is a library within Hugging Face, so it's sort of understood in the field that if you're using the transformers library, it's coming from Hugging Face. So I'm going to say from transformers, import pipeline. And pipeline is a specific set of, it's actually a function that you're calling. And what you're doing is actually, I'm creating a variable called classifier, and I'm storing the output of the function pipeline and actually identifying that I am interested most in sentiment analysis. Now what this does is essentially load a pre-trained model for sentiment analysis. Next, I'm going to get the result of that classifier, and now what we do is we take that classifier and we actually feed it a specific type of user input. So I'm going to use the answer or the question, I love learning how to make robotic sentience. So I just realized it's not a question, that's an exclamation. English is hard. So now let's print that result. And let's see what this looks like. So I'm going to run command, enter. And of course it has to do its thing. So when you get that little star, it again gives you insight that the code is working. It's saying that no model was actually successfully supplied. And we're running into a default distilled. Yeah, it's interesting. Okay. Pausing. Okay. Restarting this. It's actually not sentiment analysis. It's called text classification. So let's try that again. Okay, we're repausing this. So there's actually one line that you probably have to run to confirm that after we ran the pip install transformers code, you actually have to test this blob here in your terminal to make sure that it downloads the necessary tensors and config.json in your local environment. I was running into some weird errors, and this is coming from the official documentation. Basically, just make sure that you have this. I'll have this link below for you, actually, to just make sure that you guys have this resource. So now I basically am going to, again, run this chunk of code. Again, I'm using the pipeline abstract function, and I'm calling the sentiment analysis model or pre-trained model. And then the sentence that I'm putting in is, I love learning how to make robotic sentience. And actually, when I run this code, it identifies that that label is actually positive, probably because it picked up on the word, love, learning. And that score is 0.996. So it's pretty sure that that is indeed a positive sentiment. And so here you can tell that the machine tells us that our sentence overall has that positive sentiment. How cool is that? So there you have it. You've summoned the gremlins with our functions. We've unlocked the treasure chest and vortices with these modules. And we've even taught our own machine how to understand human feeling. That's the magic that happens when you experiment. So, playing around with these code snippets, making them your own, and embarking on your enchanting AI journey is just the first step. This is video 6 out of 20 in our beginner series, An Introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Happy coding, and may your code always be bug-free. Greetings, future AI wizards. Now today, we're going to be diving into the magical realm of Python data structures. This is video 7 out of 20 in our beginner series, An Introduction to AI. Now, think of these data structures as different types of containers or unique dimensions to store mission-critical information on your journey into AI wizardry. Let's just dive right into our Jupyter Lab Python notebook. Now, I'm going to assume that you already watched these videos in order, so you should probably know how to write these out. I've pre-populated some of these ahead of time, so please feel free to follow along or simply pause the video whenever you need to copy down what I've written. So let's teleport over right here. You'll notice that first we are actually importing NumPy and Pandas. These are just, again, the libraries that we mentioned earlier to make your life far more interesting and easier. So now let's take a look at the actual code blocks. First up are the lists. Lists are like magical boxes where you can actually store a collection of items in a specific order. The main thing to remember is its syntax. Now, in the syntax, lists in Python are actually ordered collections that are defined by square brackets, and they can actually contain multiple items of varying data types. Here, we're going to just have different types of strings. And so I'm going to jump in this code, and you'll see here that I've actually built a little list of founders in the AI sector. Next, we've actually added some of the key methods that are associated with lists, including appending, identifying the length, slicing, sorting, and then removing. So first, I'm going to silence the other code that's below. So let's pull that up here. That way here you can actually see what the code looks like before I do anything. So remember how we just ran the founder block above. So here you'll see I first printed it and then I added John McCarthy. So if I print again, and let me stop this one, let's see what happens. You'll now see that we have John McCarthy. This just basically adds another person or object to the end of the list. Now I'm going to actually slice the founder list and I'm going to save it to another variable. We're going to just take 2 founders from the main list, and I'm going to index it by founders1:3. This will access positions 1 and from 1 to 3, and it'll create a new list and print out those 2 founders. And so you'll see here it went 0, 1, 2, and then it ended at 3. So it sliced out Grace Hopper and Alan Turing and returned them. Finally, the next thing that we're going to do is now remove a founder. So just so you're tracking how that looks, I'm going to print right before and right after, so that way you can have a good idea of how this is actually working. So I'm going to print the original list, remove the latest object, and then we're going to print it again. And you'll see that here it errored out. And the reason why it errored out is because I did not specify who or what I was actually going to remove. And so that's important because you need to be able to know what you're actually going to cut out. And so when I want to remove out of my list, I'm going to actually name, in this case, let's throw out Alan Turing. And now when you do this, your list will isolate him. And there you have it. Those are lists. Now let's jump into number 2, tuples. Once written, tuples cannot be changed. Think of them as sealed scrolls. In this case, tuples are immutable collections that are defined by these parentheses. And when I say immutable, that essentially means that, again, their content cannot be changed after creation. Now, while they're immutable, there are 2 types of unique methods that you can always use with tuples, and we're going to go into them. First is the idea of counting. The counting spell, or counting spell, basically allows you to tell how many times a particular item will appear in the tuple. Likewise, index is a type of incantation that will reveal the position of whatever item in the tuple is that you ask. It's more easy if we just actually jump into it. So let me run this line of code, where here I built a tuple called AI topics. And then here you'll see it says AI topics, and then we want to print out what these actual AI topics look like. So I'm going to type out AI topics number 3, and you'll see that it accesses 0, 1, 2, 3. Remember, we always index at 0. And when I type in 3, it returns reinforcement learning. So again, once built, it never changes. Here, I can then test different functions for the tuples. And as I said, with counting, we would count how many objects appear in that tuple. First, let's test whether or not generative AI exists within AI topics. Then we'll get into the fun use cases where we use my sort of wizardry magic example to make it more understandable. So here you'll see, yes, indeed, generative AI is in AI topics, and so this returns true. However, if I put something in like, let's say, deep learning, which is not in that list, if you try to run that, it says false. And that's exactly what we would expect. So I'm going to now silence this, and we're going to look at my sort of witchcraft and wizardry example for us to study how this actually affects it. So here we are going to have wizardry includes a few ingredients in these sort of secret tomes of tuples. We have a basilisk scale, phoenix ash, unicorn horn, newt eye, and more phoenix ash. So I'm going to actually count, and as I said earlier, we will count how many times phoenix ash appears. The second step, and this is where indexing becomes important. Again, remember in Python, we index at 0. Here I'm saying, where is the first instance of a unicorn hair? Or actually, hang on, see a good typo, not unicorn hair, but unicorn horn. So where did we first start using the unicorn horn in this sequence of ingredients? And so what I do is actually access that index of unicorn horn. But since we index beginning with 0, I have to add 1 as another number. So when I run this block of code, it tells us that we've indeed used the phoenix ash just one time, and you'll see in the wizardry tuple that there's indeed only 1 phoenix ash. Likewise, it tells us that the unicorn horn is actually our second ingredient. And that makes sense because, again, when we index, it goes 0, 1, 2, 3, 4. And in this case, the unicorn horn in our indexing system is appearing in that following position, 0, 1, 2. Now that we've solved this, let's jump into number 3, dictionaries or our enchanted books. Now let's review the syntax. Again, dictionaries map key to values using these nice little curly braces. And then the key value pairs are separated by a simple colon. So again, in this case, neural network is the key and the value is the definition. It's pretty self-evident in the name. In other words, you can use dictionaries to map categories and labels to predictions or features to values, or really however you like it. So now I'm going to show you some interesting methods that allow you to add to the list. Unlike tuples, dictionaries can actually be augmented. And so if I actually print out the number of algorithms that we have first, you'll see an interesting output. Or print algorithms, it'll just print the entire dictionary so far. Now I'm going to hide that, and then I'm going to actually add another element to our code, and then we're going to print algorithms again. Let me actually get rid of this because I want to show you this idea first. So when I just print algorithms again, notice we successfully appended or added a key value pair to the end of the entire algorithm dictionary. Now this is a little trick that I wanted to show you because you'll start seeing it when you write code and read other people's code. When you put in a specific index, it doesn't work. But what you actually need to do is type in the name of the key, and that will allow you to access those values. So here, if I put neural network, it returns that value. But if I just put the index, it errors out because it cannot find that actual index. So when you're printing out or accessing a dictionary, you need to make sure to actually use that key. All right. Now let's move forward to our fourth example here. And here, let me just change this back so that way we don't have this annoying sort of error like floating around. Actually, what we can do, let's clear the cell. Actually, we don't have to do that. Let's just print neural network to clear that up. And now let's jump over to a few more dictionary methods. Now, if you take a quick look at the dictionary methods, and by the way, this is no longer relevant. If you hop over to dictionary methods, you'll see that we can also iterate through a dictionary. And here I've actually just listed the algorithm and the description. So we're going to print that out. And then I'm also going to show you what can happen if you get a specific algorithm. And in this case, random forest doesn't even exist. So this should produce an error and return not found. And so you'll see again that in our algorithm, we indeed iterated through each value. We printed out description, and it all worked out accordingly. Now, in this case, again, we did not find a random forest, but let me see what happens if I do algorithms get, and then let's just pull decision tree. What happens then? So here, when you do decision tree, description will just return the definition of decision tree, breaks it down step by step. But now let's imagine a case where I then bring back random forest, but I don't provide that sort of error that accompanies it. Because you might be wondering what happens here. And in that case, because I didn't provide any value, because random forest doesn't exist in the dictionary, all it does is return, unsurprisingly, none. And so hopefully that helps you understand how you can both get values specifically from a dictionary, as well as iterate through it. And again, we used a for loop that also went through every single item pairing of that dictionary. Fourth is sets. Now, we're going to look at sets, which sort of act like our unique potion bottles. Sets are particularly cool because they are indeed unordered collections of unique items. So they are also defined by curly braces like this, but their value is to actually eliminate duplicate values. Indeed, sets are like potion bottles that would refuse to hold duplicate ingredients, and they're great in AI for tasks like removing duplicate data points or labels. So in this case, let's look at tools that are common in Python, and I built a set here already, and let's print those tools. Notice that while I have PyTorch listed at the beginning and the end, in the set, because PyTorch is only counted as a unique value once, it does not appear twice in the output. And indeed, let's now compare some methods that can be applied with sets. You can either find and intersect with a set, or you can add to an existing set. And so you'll see here that I created more tools, and I list also scikit-learn and TensorFlow. And then I try to calculate what the intersection is by applying that to the original set. So I run the function and add my new set onto the existing set. And we save that to a variable called common tools, and then we output. And unsurprisingly, this should tell us that the common tool between the two sets is only TensorFlow. Finally, you'll see that I added to my set because unlike tuples, sets are actually mutable. And so if I just basically do print tools, this will be a little bit different because now we'll also have scikit-learn at the end of the set. All right, all. Now, in summary, you've learned 4 of the fundamental data structures that you need to understand how to build AI algorithms in Python. Bravo, young data wizards! You've journeyed through the enchanting realm of Python's mystical data containers, unlocked the secrets of wielding the power of lists, tuples, dictionaries, and sets like true sorcerers of code. This is video 7 out of 20 in our beginner series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will also allow you to elevate your career in tech and remain in demand on the job market. May your data always find its rightful place in these magical vessels. Greetings, digital explorers. So today, we're going to dive into the treasure troves of data files. This is video 8 out of 20 in our beginner series and introduction to AI. Now imagine that these files are ancient scrolls. They're mysterious tomes, and they are magical artifacts that hold the secrets to building powerful AI models. So first, let's jump into it. Let's start with reading and writing files in our basic scrolls. In Python, the built-in open spell actually lets you simply access these types of scrolls. So you'll notice on my screen here that I actually have the preamble. Each of these import lines already contains the necessary libraries that you'll need to handle these different file types. And I mentioned that our most trusty function is this open function. Now you'll notice here as well that I already have written a little text file known as scroll.txt. And what we're going to do is actually run this code now to print it. And then we're going to write a function that allows us to look at how to open it and write a new line into that text file. Finally, I'll then want to print just a subset of the lines in this text file. So let's see how that looks. And there you have it. This is taking a file that is currently a text file and simply printing it out into our Jupyter notebook. We are entering a magical landscape and learning how to handle files with Starbunny. All right, now I'm going to jump into the next section. Oh, and also don't forget to always close the scroll file to keep its secrets safe. So now let's jump into the world of the CSV files, which we also like to refer to as our tabulated tomes. Now here, I actually found the following CSV and podcat files from a Kaggle link that I'll attach in the comments. And here we actually list the 2023 Fortune 1000 companies with ranks of eligible companies, the revenue generated from core operations, discounted operations, and consolidated subsidiaries. The takeaway message here is that CSV files are like tomes of tables, and the CSV library helps you decipher them. I'm also going to include some code here that allows us to easily sort of open that file, and then we actually get to read each line and print out those rows. We're then going to sample and preview what that looks like, that CSV file here in our Python notebook. And then we're going to actually jump into a new tome, establish some new data where I take a name and an ability, and then I write that into a new CSV file. So we're going to execute this code now. And you'll see that there's a lot of output. The reason why this is occurring is because I had a pretty big CSV file, and I'm actually printing for every single row. So you'll notice kind of quickly, like it says 11, 12, 13. Each of these blocks in the brackets are different rows. So this is kind of excessive, but this tells us that it's working. Now that we've actually studied this, we're going to jump into the next type of file that we're interested in, known as the JSON. We'll treat these as enchanted encyclopedias. And JSON files actually store structured data, much like a sort of magical encyclopedia or grimoire. For those of you who are Harry Potter fans, the grimoire is actually what stored a lot of documents about sort of the fantastical beasts in the Harry Potter universe. Now, this JSON library, which we also installed at the beginning of this notebook, actually lets us converse with these active encyclopedias, these grimoires, and these JSONs. So I've actually also already stored this here with a sample of it, and we're going to print the knowledge that's in this grimoire. We're then going to write into that encyclopedia or grimoire a new set of knowledge. So here I'm going to open up a new grimoire, And here we're going to store information about what a mermaid is, as well as a centaur. And then we're actually going to, again, convert it back from a JSON into a data frame in Pandas to then preview. And this is what we'll get. So you'll see here, this is the output of printing our knowledge. We have Star Bunny, an elemental, a vampire, and then we actually stored our info from the new grimoire, and then we took head to basically look at the data frame that now contains this new information that we stored, the mermaid and the centaur. Now that we've done that, we're going to jump into data type number 4, which is the streaming podcat. Now, I like to think of podcat files as a sort of compressed codecs. And the general idea here is that podcat files are like these codexes or codices. They are compressed and they operate because they are often used in big data. The takeaway message at the beginner level is that there are 2 libraries, the Pandas and the PyArrow libraries, that can help you navigate them. And so here, I've actually already written the script to basically use Pandas, read that podcat file that we have. It's the same, again, Fortune 1000 companies from 2023. And we're going to use the PyArrow engine to store it into a data frame. We'll then sort of take a head or look at the top section of that data. And then we're going to write data to a new type of codex. So let's run this chunk now. And it's actually good to run into some of these errors. And it's saying that we actually don't have a module named PyArrow. So when you're missing a module, I mentioned this in one of the earlier videos, but this is actually a good sign for us to remember that we should probably import those libraries. And it looks like we can't just simply do this here. So now we have to figure out how to actually import or install PyArrow. And the best policy to do that is actually to, I'm going to move this here, go into your directory. And I'm actually going to jump into it and do pip install PyArrow. And you'll see that we are now installing that package in this environment. Let's see if it works here. And now it actually worked. So now we're going to try this again. I'm going to run this code, and you'll see it thinking, and it looks like it worked. And you might be interested in seeing what the data looks like. So let's actually split it apart and just examine what this data looks like. And here we go. This is our data from the podcat file, just the first sort of 31 columns and the first 5 rows. And so it's promising that tells us that this all worked. And to see if we wrote to a new codex, I'm actually going to just ls in the same directory. And we'll see that actually the new codex podcat, which I declared here, was also generated. And there we have it. We've actually now both learned how to read and to write in the podcat format. You also got to sort of actively decode and realize that, hey, sometimes there are packages that are missing, and you learn how to do that to quickly pip install the required file. Now we're going to handle multimedia, the more exciting and fun part with visual tricks. So let's talk about how we work with these sort of magical mirrors and portraits. So you've got images, videos, and text. And with these types of data, we typically rely on either the OpenCV library, which we also have endearingly named as CV2, and we'll also use the Pillow library, which appeared as import PIL or import pill. So in this case, I'm now going to just execute this code, and we're going to see how this looks. Let's actually clean it up as well. So let's do it first for images, and then second for video, just so that way it doesn't get too congested. So let's see if using image from the pill library will work to demonstrate Star Bunny. And we did indeed get a little pop-up of Star Bunny. So there he is on my shirt, as you can see here. And there he is again as a file. All right, and now let's take a look at let's see if we can run this doc video using OpenCV2. Let's check it out. And you'll see that actually the first frame was extracted, although it doesn't actually run the whole video. This is the first frame of the doc video. All right, so now let's see how we could actually display these images in a manner that is more lasting. So actually, let's split it up again, just so the way they don't get confused or overload on each other. So when I embed display image here, it's thinking, and let's see if we can actually render this. All right, so that is not running, so let's just break that. Maybe we won't run display. Let's actually clear this cell. We'll interrupt that kernel. And let's try running just the video and embed it. Let's see how this looks. All right, it looks like something got hung up. So let's see. I have a suspicion. It might be because, hang on, let's pause this. Okay, so we just went through how to actually preview Starbunny the image. And now we're going to click on how to preview and display the underlying video. So first, let's just complete this. For those of you who are still following, we had to quickly debug a little issue we had. But this is, again, to repeat our successful Starbunny visual that completed. And now what we're going to try and do is actually embed our duck video in HTML. So let's see if we can first just display Starbunny in line. This was a success. So display image invokes, again, the pillow library to put it into your Python notebook. And now we're going to just try and embed the video here. So let's see if this works. And there you have it. When you click on it, our beautiful taxidermy duck shows up. All right. With these additions, you now have the power to not only import various data types, but also you got to see a sneak peek at their contents right within your Jupyter notebook. You all even got a chance to see Starbunny, our mascot, for this beginner series on AI. You've journeyed through Python's file handling catacombs, deciphering ancient scrolls as text. You've tabulated tomes as CVs, grimoires and encyclopedias as JSONs. You've compressed codexes or codices as Podcat files, and even peered into magical mirrors for images of Starbunny and videos of a taxidermy duck. This is video 8 out of 20 in our beginner series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand in the job market. Remember, the best way to get better at this craft is to experiment. So I recommend that you start playing with these code blocks, and soon you'll be casting spells you never knew how to handle. In no time, you'll be ready to unearth AI's deepest secrets and craft spells of your own. Welcome, future AI whisperers, to the magical realm of Numpy. Now, this is video 9 out of 20 in our beginner series and introduction to AI. Now, all those neural network concepts store weights, biases, and even information within their architecture as numbers. So you might be wondering, what is Numpy anyway? Well, Numpy is short for numerical Python, and it is a library that gives Python the power to work with large arrays and matrices of different types of numerical data. And this is essential for computer vision tasks. Likewise, in the realm of language processing, NumPy arrays hold the power to represent words and sentences as numerical vectors, making it indispensable for natural language processing and generative AI. Whether you're conjuring word embeddings or crafting generative spells, NumPy is the underlying sorcery that makes it all possible. So let's jump to the code. First, I'm going to create this import script. This essentially, as we've done in previous exercises, allows you to unleash the first step to wielding the magic behind NumPy. Now, you might be wondering why we care about NumPy for machine learning. And the answer is that in the world of computer vision, we are able to actually use these to represent data as arrays. So let's jump into the concept of arrays. The array is a data structure that is at the heart of NumPy. Simply put, an array is a grid value, all of the same type. Let's make one right now together, and then let me print its dimensionality. Here, you're seeing it as open bracket 0, 2, 4, 6. And from here, you have a 1D array, which is like a row. But why don't we add another row and make it a two-dimensional algorithm? This will look like this. Notice that there's actually two brackets where each of these is basically a smaller row that then stacks on top of each other. So let's print this, and you'll see that now we have two-dimensional arrays. And there you have it. Suddenly, we can now enjoy our 2D matrix. Also notice that unlike our first example, I actually have the two brackets here. And this is the concept of nesting. But essentially, you're not only defining the matrix, you're also illustrating how your matrix nests within itself. So there are two brackets in the 2D array, and there was only one initial bracket in the 1D array. This will become key in more advanced classes, but for now, let's turn to the 5 main functions and operations that you'll definitely want to know how to do work with in NumPy. First, we'll quickly teach you the magical spell to quickly discover your array's current shape, and then the method to reshape it to your liking. The general rule is that we use rows, then columns as our rulebook. Therefore, if you print out the following shape, it will say 3, 2, which tells us that we have 3 rows and 2 columns in our data. So now, we'll simply reshape our matrix, and maybe you can even take a look at it this time to instead have 2 rows and 3 columns. So here I'm reshaping it. And you'll notice actually that there was weird syntax, so this is good. Let me just use a different name. We'll call it two-dim reshape. And then let me also change the name of this object to print out that two-dimensional reshape. And you'll now see that in this action, you transformed your array's shape like magic. Now, the second most common task that often gets forgotten or ignored is the need to conjure arrays filled with zeros and ones. So here's how we do it. I'll call this the zero matrix. You call the NumPy library and you just call it zeros. And then you can actually define it to have 2's inside of it. So there we go. And then I'll print zeros. Sorry, zero matrix. And you'll see that we created this. Similarly, we can also create a 1 matrix, which is literally the same thing, except you do NP 1s. And we can also populate it just like this. And if you want to print it again and just check it out, this is what it looks like. Now, it might not be apparent just yet, but this is perfect for initializing those vector or image masks and filters that you'll be using later in your journey. Now, the third operation that NumPy commonly relies on is performing arithmetic operations, but without those super annoying loops. Now, of course, there are some rules that you've got to know from linear algebra, but they're pretty common sense. Like, the matrices just have to be compatible. So, let's take a quick look and make some matrices. Let's bind to our A variable an array that is a simple row of 2, 2, and 2. And then let's also create and bind an array to variable B. And let's call it 8, 8, 8. Pretty much, I can just add these two because they have the same dimensionality. And voila, 2 plus 8 is 10, and we have 3 10s. Notice how you didn't have to actually make a for loop to iterate through each element or row. It's awesome. It's sort of like having little math elves and the machine doing the math for you. Okay, so now the fourth operation that you'll learn is something known as the dot product, a go-to spell for common matrix magic. So let's hop in, and this time, let me show you what happens if you click on output.ab. If I simply take the output of those variables above, you then actually multiply all of them together to get 48. Now, I can't stress this enough, and it might seem basic now, But this operation is pretty critical for any type of neural network computation. And now we're at the final step. And this is about how we can actually slice through those matrices to allow peering into underlying sections of your array with a method known as slicing. So I'm going to create a new matrix. We'll call him matrix, very creative. And then I'll define a new array. We'll make him 2 dimensions. And we'll make it pretty standard. We'll just count up to 6. Great. 7, 8, 9. Nice. And now if I print out on this matrix, let's say that I want to just slice out the first 2 values, and then from 1 to 3. Let's check out what that looks like. And here, you've successfully extracted a subsection of your common matrix, getting a 3 by 3 counting matrix. Because now we simply returned 2 to 3 and then 5 to 6 of that broader matrix. All right, this is video 9 out of 20 in our beginner series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. And there you have it, AI Whisperers. With the power of NumPy, you have now become appropriately equipped to conjure the initial steps for computer vision and natural language processing. Dive into the world of vectorized images, sentences, matrices, and algorithms, and let your AI engineering journey begin. Hello again, advanced AI arcane artists. Are you ready to dive deeper into the arcane arts of NumPy? This is video 10 out of 20 in our beginner series and introduction to AI. Now in the last video, we unlocked the basics of NumPy. This time, we're going to venture into the advanced spells and methods that power neural networks and AI wonders. The first is the arcane art of magical extraction from an array. Now you did this last time with me, where slicing and indexing are like extracting a specific potion or ingredient from a magical recipe. You'll see how we can create sub-matrices, which might feel like a review, but then I'll show you the concept of indexing, which allows you to return a very specific element. So again, first we're going to import the NumPy library as NP, and now I'm going to create a 2D array. So we'll name it matrix. As you guys remember, you need the 2 brackets for a 2D array. And let's populate it with our favorite sequence from 1 through 9. All right. Now that we've created this, I'm going to actually begin slicing it. So when I'm slicing it, we're going to call it the submatrix. And what I'm doing here is I'm actually going to just do mtx. And like in the similar example, we'll just pull out 0 to 2. And then I'm going to write comma, and then 1 to 3. This will then allow me to print that sub-matrix, or sub-mtx. Next to it, I'm also going to show you how indexing looks. So if I click on element, and then I do mtx, and we'll just look at 1 and 2, we'll print, and then that element. And you know what? Why don't we also print the regular matrix, so you can see how all of these compare. All right, so let's take a quick look at what that matrix does when I perform these types of operations. What you should understand is that there are more advanced mathematical functions as neural networks thrive on math. But first, let's dig into what this means with slicing and indexing. When I called upon 0:2, what ended up happening here is that the first value that returned was actually 2, 3, and then I also called on 1:3, which returned 5 and 6. And so what this is telling me, what it's pulling out, if this makes sense to you, is that it's saying, hey, let's slice out just the submatrix of essentially the last 2 columns. And that's what you're seeing here when you see I only return 2, 3, 5, 6. I'm going to hover my mouse So you'll see what I returned were only these two sections of the full matrix. That's all that we sliced when we designated 0:2 and 1.3. And so again, what this did was it basically told us, let's ignore this outer element of 1, 4, 7, 8, and 9. Finally, with the element of matrix 1, 2, what this did was it basically went into the first row, and then it also went into the second index of the column. And so remember that these index based off 0, 1, 2, so the first row is actually this one, and then 2 is referring to this value, because again, remember that in NumPy, you index beginning at 0. So 4 would have been 0, 5 would have been 1, and 6 would have been 2. So matrix 1, 2 pulls technically the last column, and then 1 refers to this, in other words, the middle row. Because when you index these, this row is referenced as 0, this row is referenced as 1, and this row is referenced as 2. Hopefully that makes a little bit more sense. Remember, the part that makes this a little bit tricky is knowing that indexing always begins at 0. So it does throw off some people. So now I'll quickly surface element-wise and matrix-wise multiplication, followed by conducting an exponential operation. So let's pull this out, and let's just show you what it looks like to perform, element-wise multiplication. So we'll use our trusty variables of A and B, again, 2, 4, 6, and then B, 5, 10, 15. Why not? So then the multiple result, or the multiplication result, you can actually just call NP and then multiply AB. And then you can actually print res. So here you'll see that we multiplied each of these with each other. Element-wise, so we got 2 times 5 is 10, 4 times 10 is 40, and 6 times 15 is 90. So that makes sense. Now let's try to perform matrix multiplication. Here, if you do dot res, and then we do np dot ab, you'll do np dot res, and what you get is actually 140. So for those of you who are familiar with linear algebra, you'll recall that getting the dot product actually takes vectorized data and returns a scalar. And in this case, we got a scalar value of 140. Now, let's finally perform an exponential operation. And so I'll call it expres, and then you can actually do this with np.exp, and then we'll pass an a. And so what this does, first let me demonstrate. So print expres. What this does is actually it takes our values of 2, 4, 6 and it exponentiates it, resulting, of course, in these following values. Okay, so number 3 is like a shapeshifter spell. Let's change gears a little bit. And this is a critical concept in NumPy known as broadcasting. Now, this capability allows arrays of different shapes to successfully interact harmoniously. So I'm going to show you what that looks like now. So I'll show you broadcasting in action. You've got a matrix. And again, we'll do our trusted sequence. 1, 2, 3, 4, 5, 6, 7, 8, 9. And look at my vector. And this will just be a single array. And now here, we'll actually take these and we'll combine both the matrix with the vector. And then we'll print the result. So as you'll see, you'll notice that you were able to actually magically shapeshift that vector to match your matrix. And all we did was actually add the vector to the matrix. That is the beauty of broadcasting. And so let me explain this one more time to make sure we're super clear. Broadcasting in NumPy allows arrays of different shapes to be used in arithmetic operations. It does this by stretching the smaller array across the larger array shape in a way that doesn't actually use extra memory or duplicate data. Essentially, the smaller array is virtually replicated to match the shape of the larger array so that they can be compatible for element-wise operations. So, in the above example, the smaller array, or vector, was virtually replicated to match the shape of the larger array matrix so that they could be added together. Okay, now we're going to change course again and focus on number 4, which is the beauty of a locator charm. It's helpful when you need to find literally where a specific element in your matrix is based on unique conditions. So I'm going to call this Boolean indexing. So I can call it data, and I'm going to bind another matrix here. And in that array, I'll just build it incrementing by tens, and it'll just be a singular vector. And then what we're going to do is we'll call it filtered, and I'll call this filtered data. But what you then do is you actually establish the conditions. So you only want data that will be greater than 35. Does that make sense? And so I actually pass that as the input to data. And then if you print filtered, let's check out what we get. And there you have it. You actually only return the last two values of 40 and 50 because they satisfy the requirement of being greater than 35. Notice that with this charm, you've been able to now filter out numbers greater than 35. Now, number 5 is probably the most interesting. This is how we simulate tweaking neural network weights as an application of some basic concepts that you saw earlier. So first I'm going to initialize new weights. And let's scroll down so you can see everything. Weights equals np random, and I'll do random 5. Now, just so you have awareness, we're going to add some text as well. So original weights. And then I'll call those values here weights. Just so, let's see, and we got a little error here. Interesting. Looks like the random field is not working for us. How weird is that? We might not need that anymore. It's because I typed it out wrong. It's a subfunction of random. My bad, team. So now if you click out on weights equals np.random.randn, and then you run it as 5, you'll see that we then stored it as a vector of 5 values, 1, 2, 3, 4, 5. These were our original weights. And now what I'm going to do is actually bring in adjusted weights for demonstration. So we'll make up a sort of hypothetical learning rate, 0.01. We'll generate our gradient here. So I'll sort of hard code the gradient. First value being 0.5, the second value changing by minus 0.1, the third value changing by 0.8, fourth value changing by minus 0.05, and the fourth increasing by 0.9. And what you do is you actually take the weights, and this is literally what's happening. You subtract or you update them with this minus equals, and then I take the learning rate times that gradient. And then if you print that adjusted weight, then you click on weights again, you can check out what this actually looks like. And so you'll see that these values indeed were updated or changed. So just like that, you essentially took some random weights and caused the network to learn by subtracting the product of the learning rate and the gradient from the original weights. In that way, your neural network just learned and evolved. Finally, For those of you interested in running AI in sentences and language, you might also be interested in understanding how we can vectorize a sentence as our sixth hint in this video. So we can do this by vectorizing a sentence in the following example. And again, when I say I'm vectorizing a sentence, that actually means that I'm converting its words into numerical representations, often using pre-trained embeddings or simple one-hot encoding. So first you got a sample sentence. Let's say sentence equals, I am learning AI. And then here you want to convert to a one-hot encoded vector. So what we do is we take vocab, and then you can actually call the function sorted. We use a set, which is a type of dictionary-like structure. I take my sentence, and then I split it. So the split allows me to actually split it based off each of the gaps in each of the token words. And then in one-hot vectors, I then initialize, like you saw in earlier examples, my zeros matrix, and I want it to be the length of the sentence, but then I also split it again. And so you'll see that you also want the one-hot vector to have the dimensionality of both the length of the vocab for its columns and then the length of its sentences for its rows. And then what happens here is I want to iterate. So for every I and a word in our now enumerated sentence, you basically want to iterate and populate those new values. So one-hot vectors, and I just realized I typoed, so let's fix that. One-hot vectors. I, vocab, index, word. And I want to set that equal to 1. And now this should actually print those one-hot vectors. And you'll see that we actually changed it into a representation where each of these captures one of these words. I am learning AI. So in this example, we've used one-hot encoding to vectorize the sentence. Each word in the sentence is represented by a vector, where only one element is hot or set to 1, while the rest are cold or set to 0. The position of the hot element corresponds to the word's position in our vocabulary. Now, one-hot encoding is a method of representing categorical data as binary vectors, where each category is mapped to a unique vector, with all zeros except for a single 1 at the category's index. Now, we use it because many machine learning algorithms and neural networks require numerical input features, and one-hot encoding provides a way to convert categorical data into a format that can be fed into these models without reintroducing ordinal relationships that aren't present in the original data. Behind the scenes, for each unique category or label in the dataset, a new binary column is created, and each instance is marked with a 1 or 0, depending on whether it possesses that label or not. All right, AI arcane alchemists, you've journeyed deeper into the Numpy labyrinth, mastering smells and incantations that are the backbone of applied AI engineering. As you venture forth, remember, the true magic lies in experimentation. This is video 10 out of 20 in our beginner series and introduction to AI. By the end of this series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Now roll up those sleeves, dive into the code, and let your AI dreams take flight. Until next time, may your algorithms be ever insightful and your code ever bug-free. Hello everyone, and welcome back to this channel. Today, we're diving into the exciting world of pandas in Python. Whether you're an aspiring computer vision guru or a large language model wizard, this video is your golden ticket. So let's make data fun and understandable. Now, you've just learned about NumPy if you watched the other two videos, and now we're going to switch over to Pandas, another vital library that is incredibly helpful for individuals who work in this sector. This is video 11 out of 20 in our beginner series and introduction to AI. Now, Pandas is a powerhouse in data manipulation and analysis in Python. It's like the Swiss Army knife for data scientists and engineers. But why Pandas, you ask? Well, it's simple, efficient, and versatile, making it perfect for handling large datasets, just like the ones you'll encounter in AI work. Now, in the world of Pandas, everything revolves around series and data frames. Think of a series as a single column of data, while a data frame is like the whole table with rows and columns that are filled with data. It's like the building blocks for your data empire. So first, let's look at some basic Pandas operations, and let's get our hands dirty by creating a series and data frame from scratch. So again, we're going to import the library pandas as PD as step 0. Now, we'll first create our series. So I'll call it data series, and you basically invoke the object from the pandas library with pd.series, and then you can populate it. So here, let's just go up to 4, and then you can print that data series. And boom, you actually just created it as essentially a column, and it even tells you the D type of int64. What's interesting is on the left-hand side, this is telling you the different types of indexes that accompany your data. So remember how in the last 2 videos, I was also talking about how in all these data structures, indexing starts with 0? That's exactly the position of this value of 1. In other words, 1 is indexed at 0, 2 is indexed in the position of the first position, and so forth with 3 and 4. Now, let's actually dive a little bit further into creating your data frame. So, data frame, similarly, I just invoke it from the library, so it's data frame. And what's fun here is you actually use curly brackets for data frames, which is fascinating because normally these denote in Python dictionaries. So we'll call this column 1. And then here, we'll call 1, 2, 3. And then let's make a second column 2, colon. Is there sort of like pseudo key value pairs, but with data frames. And now you'll see that we've actually made a whole table where, again, on the very left, you have the indices, but then at the very top for every single column, you have them named as column 1 and column 2. So you might be wondering, what is the actual difference between my series and between my data frame? Well, they primarily differ along 3 axes of dimensionality, of their ability to be manipulated, and their ultimate desired use cases. First, let's talk about the case of dimensionality. While a series, as you can see above, is single dimensional, that makes it ideal for representing a single variable's data. A data frame, by contrast, is more suitable for representing multiple variables and their relationships. Second is the axis of data manipulation. Now with a series, operations are generally per element, similar to NumPy arrays in the previous video. In contrast with the data frame, there are more complex operations like group by, pivot, and multiply dataset joins, similar to SQL operations. Third, you've got the ideal use case. Series data types in general are ideal for tasks that require a single uniform column of data that stores output of a single feature from a dataset. Meanwhile, a data frame is used in scenarios where multiple related data columns are required to perform more complex data analyses and manipulations. So now, let's actually build an example of using data that might be relevant in a computer vision application. Pandas helps you manipulate image metadata or results from the image processing algorithms efficiently. So I'm going to call this our example for image and metadata storage. So we'll call it image_data, and I'm going to actually just build it with file name. You can tell that we're building a data frame here, and then the value that corresponds to this will be image1 JPEG, and then image2 JPEG. Again, we're just making these up, but this is supposed to sort of give you a little bit more detail about a possible use case. 1024, 248, common image structure, and then finally the third column will be the height. All right. Oh, and of course, I messed that up just a little bit. There you go. And now if you want to actually check out the data frame for those images, what we all have to do is basically bind that image data structure into the Pandas data frame. So first I basically populated the data and then I passed it into the data frame, which you're seeing right here. And then you can actually print data frame images. Boom. So imagine sorting, filtering, or even analyzing thousands of images with just a few lines of code. Now, even more time relevant, let's hop to some examples that demonstrate how Pandas can be used for GenAI and LLM unique use cases. Here, data preprocessing and analysis are crucial. Pandas could actually really help you in organizing and preprocessing training data for these types of models. So here, I'm going to now walk through another example of possibly preprocessing text data for a potential LLM. So what we're going to do now is we'll take text data, and similar to the data frame above, we'll create an ID. I'll just simplify it with indexes 1 and 2, referring to their identity. And then I'll actually bind that to some text values here, where got text, colon, and then what we actually care about here is a text blob. In this case, we'll call the first one hello world in the index, and the second one, let's say pandas is the best. All right, so now you've got df text, data frame text, and then what I do is I take that pandas data frame and I pass text data into that data frame. So when I print df text, voila, you now have your data frame that structures these text bodies based off of a provided ID. And that's a wrap on Pandas in Python. Remember that this is just the beginning. Dive into the documentation, experiment with your datasets, and keep exploring. If you love this video, smash that like button, subscribe for more, and let us know what you want to learn in the comments below. Stay curious and keep coding, friends. This is video 11 out of 20 in our beginner series on Introduction to AI. By the end of this series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Hey, brilliant minds! Backed by popular demand, we are diving deeper into the world of Pandas in Python. So today's mission: mastering filtering, sorting, grouping, and tackling missing data. This is video 12 out of 20 in our beginner series and Introduction to AI. Ready to level up your data game? Let's roll. So Pandas isn't just about holding data, it's about making it dance to your tune. Let's start with filtering, sorting, and grouping, the bread and butter of data manipulation. So first, I'm going to import our trusted packages of Pandas and Numpy. And then what we're going to do is we'll actually create an example data frame. So this should be able to have enough parameters to sort of teach you these concepts, at least for the first 3. So we'll create 3 people with names. We'll name them Alice. We'll name them Bob. And we'll name them Charlie. Pretty basic. We'll give them ages as well. We'll make them 25, 30, and 35. And we'll put them in cities. What city do they live in? Let's say they live in New York. Oh, let's bind that to a string. Bob is in LA. And Charlie is in SF. So first, let's just print this to make sure we're all happy with how this data structure looks like. And you can see we have essentially 3 rows and 3 columns. So that's great. So first, let's now review this concept of filtering. So with filtering, you can actually just filter out based off Boolean rules that you pass into the data frame. So I can access the data frame, and then I put in the rule here. So let's say I want to look for people who are young, and I define that as people who are under the age of 30. So then I do data frame, open bracket, and then data frame. This time, run the logic along just the age axis, and I'm looking for all people who are under 30. And then depending on how that looks, you will then print out the variable for young folks. And it makes sense. We only get Alice because she's the only one who is under 30. Now let's study the concept of sorting. So it's sorted based off of age as well. So if I sort the values, and then you can actually define by, and in this case, we have our axes for age, and then you can print sorted data frame. If I print that, it will have the exact same order that we have here. Now, of course, that doesn't really show you anything because our original data set was already sorted. So why don't we switch Bob and Charlie? So I'll put Charlie here. I'll put Bob here. 35, 30. And Charlie was in SF and Bob was in LA. So let's re-replicate that. So now you have out of order, but then when I sort it, it's in the same order. And so that sort of shows you that you're able to actually restructure the whole data set over one singular axis. All right. Now, finally, let's look at this concept of grouping. Now, essentially, I can group people based off of their underlying city. So if I do grouped DF, I can do this by group I. In this case, we'll sort them by their city. And in this case, you can do it by mean. And then you can print grouped DF. And so this one is just a little bit weird because here we now have their cities, but then you pulled the mean value, which came from also their accompanying ages. And so this is a little bit strange, but in general, grouping is another way to basically pull out specific values. And in this case, we pulled out that value of city. All right, this was simple yet powerful. You've learned how to filter the young, you figured out how to sort by age, and you even grouped by city. So now let's address the elephant in the room, missing data. It's like a puzzle with missing pieces, but fear not. With Pandas, you can find those pieces or make new ones. So first, let me create a sort of emptied out data frame. And honestly, if you're working with dirty data in the wild, you're more likely to run into these types of situations. So we'll even create one that didn't have a user. And then let's create ages as well, similar to the last one, or the last example we had. But this time, let's only give Blake an age, whereas some of our other people, let's just fill it in with not a number. And again, this is something that you're likely to encounter in the wild when you're working with sort of unclean data sets, or you're working with survey data, or the company that you're working for just happened to gather data from users, but the users didn't fill everything out properly. And so now if I print this data frame, df empty, you'll see that I have one value that's just empty with no name, and I have two not a number values. So now that that's the case, let's figure out how we can actually fill in the missing values with a replacement. So first, I'm going to show you how to fill it out with a replacement. And we'll do df filled equals df empty. And I can actually replace. And let's just say I have another data set that tells me that that empty string is actually a human being known as Margie. So now I can actually just print that new df filled matrix. And you'll see, unlike the previous example, we now have a value that's been replaced in the second row for Margie. Great, so that's how replacement works. Now let's take a quick look at how we could run dropping rows with missing values. So sometimes you just don't want to deal with values that have not a number. So let's take the empty data frame and I can just drop that. And basically if I drop any of those rows that have the missing value, then all you'll get is the value for Blake because the other two had not a number.
So that's unfortunate, but that is one way to address not a number values in a data frame. Finally, the third thing that you can do is something more fancy known as imputation. So here, what I can do is actually print. What I can actually do is I can take my empty matrix and we can take the age that's available. And what I can do is actually fill all those values of age, specifically fill those on numbers with our mean age. And so this is interesting, right? Because the way that you would calculate the mean age is to simply take that value that we calculated earlier using the mean calculation. So let's fill this out, and then I'll print it actually, so that way you have a visible indicator. And actually, one thing that I just realized, one key element that you want to throw in is actually you have to populate that mean age variable. So let's take df empty. And even though we have one value, we'll have to still run the mean function on it. This will, of course, return 24 because there's only one number that I can use. But now, you'll see that my mean age was 24. And then you'll see that at least for the age matrix, I was able to substitute all three values with 24. And so finally, to wrap this up, if I basically print df empty, now we now have filled all those values with 24. And there you have it. Whether or not it's filling gaps, dropping them, or smart imputation, Pandas has your back. And as you can see, part of the problem is not just learning the syntax, it's also having the wisdom and understanding of when to use certain methods as well as the context. This is video 12 out of 20 in our beginner series and an introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market.
This is video 13 out of 20 in our beginner series and introduction to AI. So first things first, what exactly is OpenCV? Well, as you can see here on this website, OpenCV stands for Open Source Computer Vision Library, and it's a huge open source library for computer vision, machine learning, and image processing. So OpenCV actually supports a variety of languages, but today we're going to focus on Python because of its simplicity and its readability. So I'll show you this website really quickly. And the idea is that there are many resources online, including documentation and even a history of different types of documentation with the different versions of OpenCV that are available. There's also a really great sort of get started installation pathway for you to learn how to actually navigate through this tool. The fact is, whether it's facial recognition in your phone or autonomous cars, OpenCV is the backbone of these technologies. So let's explore why OpenCV is like a game changer in computer vision. Now, like a Swiss Army knife for computer vision engineers, OpenCV is fast, efficient, and versatile. In fact, it's packed with over 2,500 algorithms. These algorithms can detect faces and recognize them, identify objects, even possibly classify human actions, and track moving objects. So another reason that you might like to use OpenCV is that it's actually cross-platform, which means that you can use it on Windows, on Linux, and on Mac. Plus, as I've already shown you, it's actually open source. So let's sort of just dive right into it, and I'll get you right into the setup. So first, what you want to make sure to do is that you actually have Python installed. So let's walk through that setup. You want to, in your command line here, and I'm going to open up a new screen, simply check to see if you have that. So we're going to do pip install OpenCV-Python.
And so for me, it looks like it's actually updating it, but it says that, I had the requirement already satisfied for one of the dependency packages here, NumPy greater than 1.17 version. Anyway, I already had it, but for you, it might take a little bit of a while. But once you have it, you will now be ready to conquer your world with computer vision. So let's move on to the fun part, which is reading and displaying, as well as saving images. So first things first, let's actually just jump right into a sample here. First, you'd want to type in the simple code block to make sure that we've imported it into our local environment. We can use the shortcut import CV2. Also, just for plotting purposes, let's use PyPlot, because I've just noticed that makes it a little bit easier when we're working in this beautiful Jupyter environment. All right, and it's actually saying that I don't have a package named matplotlib. So when that happens, we can simply do pip install matplotlib. And it looks like there were indeed some issues. I might have updated my version, and let's try that again. All right, everything's working, guys. We are all good. So now let's hop into loading in our new image. So the way that you typically do this, and it's pretty straightforward, but let's start a new column, and let's type in image. So what we're doing here is we're actually taking the CV2 library, we're invoking a method called ImageRead, and then in that path, I actually already saved an image called sample.jpg. And like any good function, you close it, and then we bind it to image. So I've saved this. Did it run? Let's check. Yes, we're all good. So then let's try to plot it and see what is that image. So what you now do, remember we installed matplotlib. So then you go plot, invoke the image show, and then we pass as the variable image, which we just did in the line above. And it looks like we've got this beautiful cat. Now, here's our next question. How do you actually save that image? Well, that's great. The way that we actually save this image is, again, invoke the computer vision library, CV2. This time, instead of imread for image read, we're going to use imwrite to write that image. And I'll call this, let's call it sample 10. And then we'll save it again as a JPEG. This binds the name of the variable. This is actually the path to the image that you want to save. And then we have to pass that same variable again. So, it said true, which indicates that something worked. So now let's check out if it actually stuck. So I have to go into my projects folder, where this directory that we're accessing is hosted. And if I open that, we can see, and I've got a bunch of other files here too, but you'll see sample 10 actually was saved. And if you want to look at my timestamps, it's at 8:32, and yeah, just about 1 minute ago, we saved this beautiful sample 10 image. So we successfully sort of read, loaded, and saved. All right, now let's mix it up with a challenge. Can you guys load, display, and save this image in under 60 seconds? Let's try it out. So, ready, set, go. Okay, time's up. How did you do? Let us know in the comments and let me know if you have questions. That's a wrap on our quick intro to OpenCV. Now you're well on your way to becoming a computer vision guru. So you also have to remember that practice makes perfect. And now that you know where to find the documentation, you can actually experiment with different images and functions. Keep learning, keep coding, and most importantly, have fun with it. Now, if you enjoyed this video, smash that like button, hit subscribe, and ring that bell for more awesome content. See you in the next one.
Images are everywhere, from social media to medical imaging. But how do computers see and actually understand them? Let's dive into the basics of image processing. This is video 14 out of 20 in our beginner series and introduction to AI. Now let's start off with the understanding about how images are simply a matrix of pixel values. Each pixel actually represents the smallest unit of an image, and has a value that indicates its color. In this code sample that you can see in the first cell, I'm importing CV2, which is one of the most common libraries that we use for image processing in computer vision. Then we can load an image, and the image that we're going to load today for purposes of explaining some of these concepts are actually the star bunny image here. In case you haven't noticed, this image is actually the raw source of the shirt that I'm wearing and have been wearing throughout this series. If you're interested, hit me up and we can definitely hook you up with some more star bunny merch. But diving right back into it, let's actually dive into what it means to look at the underlying image variable. As you can see, imRead is a function that is derived from CV2, and I save this actual image to that variable, also ironically named image. Now, if I actually print image.shape, what this does is it actually returns the underlying channels for our raw star bunny. And specifically, the way that those outputs are taken apart are that the first value will be the height, the second value will be the width, and then the third will actually be those different channels. And so what you're seeing here are that we have a 1024 by 1024 image, height and width, and there are 3 channels, R, G, and B. So let's dive a little bit more into what RGB means. And in specific, we'll study this by first looking and comparing the star bunny image when it is set to a gray scale, and then we will compare it against its raw blue, green, and red values. So first I'm going to import Numpy because some of these do have dependencies with Numpy. And now we'll run the CV2 function, CV2color, in 2 ways, saving the values to gray and HSV. And so you're seeing here that, again, it's keeping the structure, but when I cast it to gray, you actually lose the underlying third element because now there's no longer any RGB. There's only one dimensionality. Does that make sense? So gray will not have 3 color channels because there are no colors. So now I'm going to run this here. This is actually showing you what the second channel looks like. And again, remember how there are 3 channels? So let's go to the earlier one, and you'll see very nicely that if I index, remember, again, 0 is actually the first channel, 1 is the second channel, and 2 is the third channel. There are distinct and different values for every one of those 1024 by 1024 pixels. These are how the star bunny image is actually numerically represented. Isn't that weird? So now what I'm going to do is I'm going to take RGB, or GBR really, and split those into different values using the cv2.split function. So I'm going to run this now. So basically, blue would have been the first, green, as you saw earlier, would be this channel, and then red would be this channel. And I've now saved them to these particular variables to take home this message. Now what we're going to do is I'm going to then merge those images back into a new image titled Blue Bunny, Green Bunny, and Red Bunny. And I'm going to fill all the remaining other channels with just zeros. That way, only one channel is expressed. And then we're going to print using cv2im show blue, green, and red bunny. So let's take a look and see what this generates. So you'll see that this is actually what red bunny shows off. Interesting, no? Likewise, this is what green bunny shows. And unsurprisingly, this is what we get with blue bunny. It's pretty straightforward. And so let's dive a little bit into the actual science. We're going to jump back a few cells to look at just the underlying grayscale histogram. Not Instagram, histogram. Too much social media. So if you take a quick look here, you'll actually see that when we examine the pixel intensity by frequency, this is a unique structure that captures the grayscale histogram of pixel intensity and its corresponding frequency for the original star bunny image. For those of you who remember, gray was actually this original value here, where we took our older image, that is the star bunny, and I cast it to a singular channel for then plotting purposes.
And so if you're curious, we can also then look at an equalized version of this histogram. So I'm going to now run this cell. And this is what an equalized image of Star Bunny looks like. Pretty mystical, no? In general, we can always work with these types of variables. And actually, in this final section, you can even run something called convert scale absolute value, and you can designate alpha and beta parameters. In this way, you can even increase the brightness of the underlying image. And in this case, what we did with the brightened image is actually increase it. And again, this is the brightened image compared to our original image. Like they say, a picture is worth 1,000 words. And it's surprisingly helpful to actually learn more about computer vision by understanding these underlying principles. I personally believe that it's crucial for us to learn how to play with them. Another key thing that I'd like to highlight is that contrast is the difference between the darkest and lightest parts of the image. So, high contrast images have usually wide ranges of pixel values, while low contrast images have values that are clustered together. You also might be wondering, looking back, why did we actually run this cell, the histogram for equalization, or equalization? The reason why you equalize histograms is specifically to enhance image contrast. The reason why is because this redistributes pixel intensities to utilize their full possible range. So, if you actually want an additional comparison, let me give you another side-by-side, because sometimes it's not apparent when you only look at one version of the image versus a second. This is, again, your equalized image, and this was actually the original image. And so you can see that when we equalize the image, we try to actually reduce that pixel contrast. But then that phenomenon of looking at an image with less pixel contrast makes it seem like it's a little bit brighter, that being the image on the right. And again, many of us tend to think that brightness refers to the overall lightness or darkness of an image. Thus, with the final line code, where we increase the brightness of the image, that can sometimes help you make details more visible. These are only beginning concepts, but if you're interested in learning more, and potentially even subscribing into my intermediate class, please feel free to hit me up or follow the website. This is video 14 out of 20 in our beginner series, An Introduction to AI. By the end of this series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand in the job market. Understanding the basics of image processing is just the first step in the journey of computer vision. As you delve deeper, you'll uncover the magic of how machines interpret visual data. Now, manipulating images is a foundational skill in computer vision. Today, we're going to explore how to resize, crop, rotate, and even draw on images using OpenCV. This is video 15 out of 20 in our beginner series, An Introduction to AI. Now, let's take a quick look at this first function. If you look at this cell here, I've decided to this time import both CV2 and matplotlib pyplot. This is basically used to take the images that we generate using the CV2 library, and in the convenience of the Jupyter notebook, I'm going to simply pass it to the plot method and then show it off here. That way all of our results will remain in the same notebook instead of popping up in different sort of files that we saw in the last video. Now, let's take a quick look and run through this entire sequence. You'll notice that the logic behind this code block is pretty straightforward. First, I use the CV2 library, I call upon the image read method, and I load the StarBenny JPEG to this image variable. The image variable is then passed to the resize method, and this time given the parameters of 300 and 200 to resize it, and then saved to the variable resized. Then, in these last two segments, they simply allow me to plot the image, and voila! When we run this cell, you'll see that in the original StarBunny image, we have, as expected, a 1024 by 1024 composition, but in the resized StarBunny, we now actually have the image quality both compressed and the dimensionality in the plot totally matches what we expect.
In other words, this is evidence that we have been truly seeking to demonstrate that resizing clearly changes the image's dimensions, and whether or not you're scaling up or down, OpenCV makes this very simple. So now let's move over to the next block. This is a vestige from another script. And now let's look at the concept of cropping. Now in general, the cropping logic is basically defining the subsection of both the y slice, or the y-axis slice, and then the x-axis slice. So I randomly chose these two different segments, and then I'm going to crop a different part of Starbuddy and illustrate it. And it looks like we just got a really nice sort of starry night. You don't even see Starbuddy in this image. Cropping allows us to extract a region of interest from the image. And as you can see in the syntax, it's as simple as slicing in Python. Now this is where things get really interesting. Rotating an image is what we are now going to demonstrate next. As you can see here, I actually am going to take the raw image of Starbuddy, and then what I do is I have to identify its center. What you might be wondering is, what are these brackets that follow image.shape? Well, if you remember what image shape returns, you'll recall that actually image.shape returned the height, the width, and then the number of channels. When you pull the index of the dictionary value shape open bracket 0 close bracket, that gives us the height or width, and then shape open bracket 1 gives us the other corresponding height or width. Likewise, when I take both of those dimensions and then I have it in 2 or divide by 2, that brings me to the center of the image. Taking that value of the center, I then pass that into this next function of CV2 called getRotationMatrix2D, and I take those center coordinates and I pass them as the first variable. CV2's method getRotationMatrix2D then allows me to also specify the degrees of rotation I want in the second variable. In this case here, I'm passing it as 45, and then 1, which is the dimension. And so that is the value of matrix. Finally, in the rotated variable, this then passes, this stores the output of warp affine, which then takes my raw, again, image, the underlying matrix, and then, of course, the center point of shape of image.shape open bracket 1 and image.shape open bracket 0. In other words, the dimensions of the image's height and width. And so when I run this script, you'll notice that we now have a rotated star bunny. And that's too easy. But what we love about this type of script is that this actually can be used in many types of supervised machine learning tasks to help begin augmenting your underlying data stores and giving you data diversity that you might not otherwise have. So let's now keep going. In the last section, we also have to realize that in image manipulation, you can also actually draw rectangles, circles, and in general, shapes onto your star bunny. These parameters that are passed to cv2.rectangle or cv2.circle can all be applied to the image value. And of course, some of these parameters simply specify the color. For example, here, 00255, designating the color of our circle, whereas here, 02550, designating the color of some rectangle. So let's just see what this looks like, because drawing shapes can be useful for annotations, highlighting regions, or even creating masks. And as you can see here, the circle with the last channel filled in renders a blue circle, while here, the rectangle with the middle channel filled in of 255 renders a green circle. Now, let's take one final look at the ability to actually even add text to your image. One way to do this is to utilize font, and specifically call on CV2 the font Hershey simplex, which simply takes some fonted text and allows you to put text onto your underlying image, which occurs here in CV2.putText. And if I run this, you'll see that my own text with OpenCV is now articulated as well. Adding text to images can actually provide context, labels, or any other necessary information that you might expect, especially when you're working on computer vision-like algorithms. All right, team. This is video 15 out of 20 in our beginner series on Introduction to AI. By the end of this series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Mastering image manipulation is just a stepping stone in computer vision. With these skills, you're well on your way to becoming a proficient computer vision engineer. Keep experimenting and exploring with OpenCV. Hey everyone, welcome back. Now, filters and transforms are the backbone of image processing. Today, we'll dive deep into convolution, kernel operations, and the magic of Fourier and wavelet transforms. This is video 16 out of 20 in our beginner series in Introduction to AI. Now, let's start off with a very simple use case. Convolution is actually a mathematical operation that combines two sets of information. In image processing, it's all about applying a filter, also known as a kernel, to an image. So we're going to get started here by walking you through some of the underlying code. In order to do that, we're going to rely on a few libraries that we used in the past, including CV2. We're going to import matplotlib.pyplot for just simplicity of visualization in these exercises. And then we're going to use Numpy for some of the more esoteric use cases later. So first what we're going to do is load our underlying image. And the underlying image that I'm excited to bring forth is the famed star bunny that you see right here. So we're going to load using CV2. That's right, you guessed it, imread. We'll call star bunny JPEG. And this time, we're going to actually make sure that this image is only brought in at grayscale. Then we're going to actually declare our kernel as a 3x3 filter box. So the way that I define my kernel is actually using Numpy, and then I basically create a matrix of ones. What you then do is in its structure, I define it as a 3x3, as I mentioned earlier. And then when they ask me actually what kind of type will this be, I'm going to make sure they're float 32s. And after that, I want to divide them all by 9. Finally, this is the step where we actually apply convolution. Remember this because you actually could realistically be asked about the convolution process. So here you can call it by running filter 2D on the image. What you essentially do is you input the image, in this case star bunny's variable, number 1, which refers to its stride, and then kernel. Then we simply have to plot that image so that way you can see what I'm about to tell you. And we're going to actually show you the original star bunny first, and then I will show you what this looks like. There's original star bunny. Remember, we grayscaled it. And now let's look at the filtered form when we actually alter the structure. And you'll notice it's very difficult to really see any key differences here. Sorry, I'm like choking today. But the takeaway message is that there are subtle changes happening when we actually apply this filter that then render this image more useful for an algorithm. Another thing to remember is that different types of kernels actually produce different effects. You've got edge detection, blurring, and sharpening, and all of those can be achieved using very specific kernels. Now, I'm going to shift focus a little bit and draw your attention to something known as the Fourier transform. The Fourier transform is particularly important because the Fourier transform allows us to analyze the frequency components of an image. It's actually a bridge between the spatial and the frequency domains. So this is where we get a little interesting. I'm going to call the Numpy library from numpy.fastFourierTransform. You can actually import a specific algorithm, FFT2 and FFT
shift. So first what you can do is I'll actually compute our 2D Fourier from the image. So I'll call this transform. And transform will be FFT2 image. So we're passing star bunny into that variable. Then I can call it shifted, and as shifted will just simply be FFT shift of transform. Then what you really care about is the magnitude spectrum. So essentially what we have now is magnitude spectrum will be a variable that is saved from taking the log of the absolute value of that shifted value plus 1. And so you can see what this actually looks like. I'm going to let you guys discover the beauty for yourselves. So magnitude spectrum, let's name it magnitude spectrum of star bunny. There's really something in my throat. So sorry, team. Watch show. And there you have it. I'm going to actually zoom in just so you can appreciate this. It's pretty interesting. Oh, there we go. This is actually, it's sort of just centered on a nice point here. But this illustrates to you some of the underlying frequency features of that image. However, it's still a little bit confusing. I'm sure you might be wondering, how can I tell anything useful about the star bunny? Well, while this might mean something to a computer, for someone who's also querying it as a human, it's not that meaningful. It just simply looks like a random starburst. While the Fourier transformation can give us the frequency information, there's something known as the wavelet transform that does provide both frequency and spatial information. So, we're now going to shift gears just a little bit, because in the vast ocean of data, sometimes the most meaningful insights can actually come from understanding the waves in that ocean. That's where Python wavelet transforms, or PYWT, enters. Now you need to realize that wavelets are mathematical functions that can actually decompose data into different frequency components. You can think of them as a magnifying glass, revealing both the fine details and the broad strokes of a signal. So, while the popular Fourier transform gave you guys some of those frequency components, it actually lacked the ability to provide time information. Wavelets, on the other hand, offer a time-frequency view, making them incredibly versatile. So, as I said earlier, PYWT is a go-to Python library for wavelet transforms. It's pretty comprehensive and offers a wide array of wavelet functions. It's also super efficient, and it's designed with both researchers and developers in mind. You might also be wondering, why do computer vision engineers love PYWT? Well, wavelet transforms excel in tasks like image compression, denoising, and feature extraction. They can actually isolate features at different resolutions, making them invaluable for detecting patterns, whether it's a texture of a fabric or the edges of a building. In essence, PYWT offers a lens to view data in a unique way, capturing both the rhythm and the nuances. For computer vision engineers, it's not just about seeing, it's about understanding the symphony of frequencies that construct the visual world. So this is where I'm going to actually now import PYWT. And this is how you actually apply a wavelet transform back to that original image. So I'm going to store them all in a variable known as coefficients. You invoke PYWT. This is the function, DWT2, and you pass in the image as well as you specify the type of wavelet transform. In this case, we're going to just simply use a higher wavelet. Then I can decompose the coefficients value variable. I'm doing this because I already know what the output is. It's highly structured. And these basically capture the underlying frequencies of horizontal, of vertical detail, as well as an approximation of the underlying image. So we're going to run this, and then I'm going to now structure the query in a way that allows you all to see the plot. So first, I named it CA, and we'll title this approximation. And just for simplicity, I'm actually going to have it output all of the things that you will care about. So you'll get horizontal detail, vertical detail, and you'll also get diagonal detail. Just hold tight. If you find this a little bit boring, or if you're not writing this along with me, feel free to just skip ahead. Otherwise, hopefully you're typing alongside with me. This is probably not the best design pattern, but again, I am doing this for simplicity's sake. Whoops. That was vertical. Now we're doing the diagonal. I promise this is going to get really exciting in a second, because this is somewhat what the image actually sees, or more specifically, this is what an algorithm, air quote, sees after you run a wavelet transform on the image. So here's our first approximation. As you can see, it looks very similar to our original star bunny. Let's look at the horizontal detail now. You can kind of see some interesting patterns here. If I zoom in a little bit more, you can just about make out the edges of the clouds. You can see Star Bunny's ear, his back, his nose, and some of his eye. It's pretty cool. If we swing down to vertical detail, I see other features of Star Bunny, not necessarily the same area of his back, but this time that vertical line that sort of captures his profile silhouette, a little bit of his paw, and definitely more features of his ears. Also, now we're capturing some of the interesting features of the cloud bursts and galaxy behind him. Finally, this diagonal detail is pretty crazy. I don't really know what that could be, other than maybe a possible component of Star Bunny's paws. I think this is where his paws are, but again, now I'm just sort of trying to guess at what's going on in this sea of pixels. But you can now imagine that when you look at this diagonal, vertical, and horizontal detail, how if you add just a little bit of noise and manipulate these variables, you can kind of understand how similar looking images can then be generated, as we're now seeing in this sort of explosion of Gen AI. They, at the end of the day, harvest and rely on some of these underlying features. So, from image compression to feature extraction, these three techniques that I just walked you through, basic filters with convolution, a fast Fourier transform with a magnitude spectrum, and wavelet extraction for horizontal, vertical, and diagonal detail, are all fundamental in computer vision. Understanding them is crucial for tasks like image construction, reconstruction, denoising, and more. This is video 16 out of 20 in our beginner series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Filters and transforms are just the tip of the iceberg. As you dive deeper into computer vision, you'll encounter more advanced techniques and applications. Keep learning and keep on experimenting. Thanks, everyone. Hi everyone, and welcome back to this series. Now, features are the building blocks of images. Today, we're going to explore how to detect, describe, and even match these features using OpenCV and TensorFlow. This is video 17 out of 20 in our beginner series and introduction to AI. Now, edges are sudden changes in a shape, and they can be crucial for understanding its structure. I've preloaded this text here
And I'd love for you guys to either follow along with your own Jupyter notebook and feel free to let me explain to you what's actually going on. But as you can see, we've imported star bunny, again, stored to the image variable, and then we've run the canny edge detection algorithm on it. But what is canny? Well, canny is actually a popular edge detection algorithm that was used in CV and is now available in the OpenCV library. John F. Canny in 1986 developed it, and it has a multi-stage process that detects a wide range of edges in images. There are 5 key steps in using the canny algorithm, and if you choose to go into the intermediate and advanced flavors of this class, I'll go farther in detail into this. But those main 5 steps are noise reduction, gradient calculation, non-max suppression, double thresholding, and finally, edge tracking by hysteresis, which basically helps it track and connect edges. But here you have it. We are now able to actually extract the edge features using this fun and amazing library. So now let's shift over to this next cell here, where we are now focusing on something known as key points, which you'll also see in the variable nomenclature. Now, key points are unique regions in an image, like corners of a specific texture. Descriptors usually describe these key points in a way that can be invariant to scale, rotation, and illumination. So we're going to run this as well, and when you see the output, you'll find it pretty interesting, because what's going to happen is you'll suddenly see a bunch of these glowing dots. What are those? Well, what we did here, especially when we created orb equals cv2.orb_create, is we instantiated an orb object, or the oriented fast and rotated brief object. This is used to detect and compute key points and potential descriptors in the image. Parameters, such as the number of features or n features, the pyramid decimation ratio, score type, and fast threshold can all be adjusted to fine-tune the detection process. And as you can see, there appear to be many key points, not just on the star bunny itself, but also in the background, in features of the galaxy, and even in the cluster of stars that star bunny actually nests on. Overall, orb, again oriented fast and rotated brief, is a popular choice in computer vision for tasks that require feature matching, such as object detection, panorama stitching, and motion tracking, due to its great balance of performance and computational efficiency. Now that we have key points and descriptors, you can actually also match these between different types of images. This is fundamental for tasks like image stitching or object recognition. So I'm going to scroll down here now, and you'll actually see that what we do is I begin loading another image, which will be that of a cat. The sample JPEG actually comes standard with the CV2 library. And what we're going to do is basically replicate what I just did above with Star Bunny, but with this cat. And then what we're going to do is we're going to use these 3 key functions of the BF matcher, of detect and compute, and draw matches in order to actually visualize how these all overlap. And you'll see, lo and behold, there are many edges that are drawn, but they don't seem to totally line up. Even more interestingly, you'll actually notice that the dimensionality of the actual Star Bunny image is far smaller than that of the cat. And you see a lot of collisions on only one section of the cat's face. What could this mean? That's up for us to find out later. But let me unravel the magic behind 3 key amazing methods here: BF matcher, norm hamming, and draw matches. It's pretty cool. So buckle up for a quick code-packed description. So in BF matcher, which stands for brute force matcher, again right here, you can think of it as sort of like playing a memory card game, and you're flipping cards to find a matching pair. BF matcher does something similar, but actually with the features and images. So what it does is it systematically compares every feature from one image here to every feature in this image. Whether you're building a face recognition app or stitching panoramas, BF matcher is your go-to, including matching up the Star Bunny cosmic image
that I produced with the Gen AI. I think I did this actually with Midjourney almost a year ago, versus a photorealistic image of a cat. It's robust, it's straightforward, and yes, it's definitely brute force. So now let's hop into this second section here where I specify as one of the input parameters to BF-Matcher as CV2 norm Hamming. It sounds technical, right? Well, it's actually how I specify the metric for which BF-Matcher measures similarity. Now imagine you have two strings of binary code. Norm Hamming simply counts the number of different bits. Lower the count, the more similar they are. And in that way, it's like finding twins in a binary world. It's especially great for binary feature descriptors like orb because it's a speed demon in matching and making your computer vision project lightning fast. You saw how fast it took for this cell to run. And now finally, the P de resistance, CV2.draw matches. This is visually where the magic happened and where we actually elegantly displayed all these rainbow lines between the two variables. You see lines drawn between the matching features across the images. It's sort of like drawing constellations in the night sky, but again with your images. Similar to how we can use this type of algorithm to match historical photos or track objects in a video, draw matches brings these results to life, and in this case was what rendered the alignment between the sample cat and between Star Bunny's raw image. So there you have it. BF-Matcher, norm Hamming, and draw matches are three powerful tools in your OpenCV arsenal that can transform how you perceive and interact with the visual world. You'll need to dive in and experiment if you want to unleash the power of computer vision in your projects. And now let's get even more detailed. Because that's right, you've guessed it, we can also dive into different types of neural networks. And in this case, we'll dive into TensorFlow, a powerful deep learning framework that also offers tools for feature detection, especially when deep learning models are involved. Now, before we go further, I also want to make sure that you in your terminal have already installed TensorFlow with pip install TensorFlow. Pause the video if you haven't, otherwise let's continue. So I've already pre-allocated a lot of these parameters. One of the key things that I chose to modify, of course, is here you'll notice that the image that we load into pre-processing is again our Star Bunny image. I kept the target size aligned to the normal size of Star Bunny, which is a 1024 by 1024 image. And what we're essentially doing is we're loading the VGG16 pre-trained model when it was trained on the ImageNet dataset. I actually want to, before we run this cell, I also want to clarify with you two specific things. By having weights equal ImageNet pre-trained on ImageNet data, this tells you that we actually are initializing the model with weights that were learned when the model was trained on an ImageNet dataset. In that way, this is actually a form of transfer learning, where you can leverage pre-trained models to improve the performance of your model on a possibly related task. What's particularly most important is the section include top equals false. Now, false means that you do not want to include the final fully connected layers, also known as the top layers, that were originally used for classifying ImageNet images into 1,000 categories. In other words, you're loading the model without its classification layers. Now, the main reason why you actually want to load the images without its classification layers is because for the purposes of this little lecture and exercise, I'm trying to show you the value of feature extraction. By setting include underscore top equal to false, that tells us that we can now use this model as a feature extractor. Thus, the layers of VGG16 up to the point we cut it off can turn input images into complex representations that can then be used as input for your custom layers tailored to your specific task. So, without further ado, we're going to run this. And you'll see the little star tells us that it's thinking. And unfortunately, we ran into an error because, noob error, we forgot NumPy. So let's import NumPy. And now this tells you that we ran exactly one batch and this has successfully executed within 2 seconds. Pretty impressive. So let's investigate the dimensionality of this. And you'll see we have an output of our features from that block, with those features representing 1, 32, 32, 5, 12. What does that mean? Well, the first dimension is the batch size. So a batch size of 1 means that there was only one image or data point in this batch, which is correct. We only passed StarBuddy. Now, in deep learning, models often process data in batches for efficiency, but here we again just have one single image or data point. The second and third values of 32 represent the spatial dimensions of the tensor. Thus, in the context of image processing with convolutional neural networks like BGG16, this typically refers to the height and the width of the known feature map. Here, this means that each feature map is going to be 32 by 32 pixels. Finally, the fourth value of 512 tells us that in the context of the convolutional neural network, that means that the network extracted literally 512 features, and each feature formed a channel in the output tensor. In this case, 512 features were actually extracted. So enough about actually extracting the features. You're probably curious about how to visualize them. This block of code, which you can also pull from the repo or follow along with me if you pause the video and copy it, can actually be what you will utilize to visualize your TensorFlow layer of features. Some key things to note, because this does confuse some people, is that the choice of 8 for columns is totally arbitrary, and it can be adjusted based on your preferences and specific requirements on the visualization task. I simply selected this because knowing that my dimensions of the tensor were 32 by 32, 8 is a multiple of 32, and that sometimes just makes it easier to sort of visualize and space out the number of subplots. You'll actually notice here that the logic of how I begin plotting this is that I'm going to iterate across every one of those features. So I fixed to 0 because, again, there's only one dimension in the tensor. We remain flexible for the dimensionality of the tensor, 32 by 32, but then we iterate across all 512 features. And then we basically visualize what those features look like. Another key thing that you might be noticing is in fig size, I multiplied it by 1.5 for both number of rows and columns. This is simply set up because that's what I do to ensure that each subplot has enough space to display its content clearly. And that's why the scaling factor is important, because once I click on run, we will see 512 hyperparameters of StarBuddy. Aha, voila, and there you have it. I'm going to zoom in just a little bit. We'll actually zoom here so you can all sort of take a look as I scroll through, but you'll notice that it does look like a sort of Rorschach ink blot, but in some of them you can definitely tell that they're picking up on different parts of StarBuddy, while others are picking up on sort of the cosmic galaxy behind StarBuddy, and still others are picking up on things like StarBuddy's ears, StarBuddy's, I guess, front ear. Here we've even got StarBuddy's paws. And when zoomed out and holistically, it looks particularly fascinating. I think if any of you played with early forms of sort of dreaming AI algorithms back in the early 2020s and late 2010s, you'll remember that some of them seem to pick up on some of these features and generate sort of hallucinations or dreamlike images by inserting new and wondrous combinations of objects where they see these feature maps. And there you have it. As I continue scrolling through, the list just goes on. But this is commonly what you would find in the appendix of a research paper that interrogates underlying imagery. And this is pretty common in sort of an R&D scientist's workflow when he, she, or they are actually looking at, underlying image features after passing them through a convolutional model. Well, there you have it, team. This is video 17 out of 20 in our beginner series and introduction to AI. I love this stuff, and by the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Remember,
Feature detection and matching are foundational in computer vision. And whether you're building augmented reality applications, robots, or any type of AI-driven visual system, mastering these concepts is key. So dive deep, experiment, and keep building. Thanks all. Hey everyone. So object detection and tracking are at the heart of many computer vision applications. Today, we'll explore these concepts using popular frameworks like TensorFlow and PyTorch. We'll also compare the runtime of them, and we'll take a look at a more basic fundamental form of performing object detection known as a Haar cascade. This is video 18 out of 20 in our beginner series and introduction to AI. So first, let's start off with the Haar cascades. Haar cascades are machine learning object detection methods that are often used to identify objects in images or videos. Haar features are simple, rectangular patterns that can be very quickly computed in an image. What's particularly interesting is that they're actually used to capture the presence of oriented contrast between different regions in the image. Each Haar feature can be thought of as a single specialized detector that checks for the presence of specific image patterns, like edges or changes in texture. Now, there are roughly 3 basic types of Haar features: edge features that look for edges in different orientations, line features that look for lines by considering a line of pixels contrasted against neighboring lines, and finally 4 rectangle features that are more complex and involve contrasting rectangular groups of pixels. So without further ado, let's go through some of this code and also look at the runtime that it takes to run one of these Haar cascades. So when I click this, first we're going to import, as usual, CV2, and we're going to pull in matplotlib pyplot to make it a little bit easier to visualize some of the code. This cell will capture and log the time that it takes to actually run this cell. And what we do is we actually take a pre-trained Haar cascade that's been designed for face detections in this line. And it's actually, we're invoking this XML file called Haar cascade frontal face default XML. We save it to the variable face cascade, and then I pull in an image. This will be an image of myself that you can find on the open internet. And then what we do is we turn it to grayscale. From that grayscaled image of myself becomes an input here. And then I actually take the face cascade variable and then I call detect multiscale onto that face cascade. And so basically I then pull the X, the Y, the width, and the height in this faces algorithm, and I draw a box around my face. So as we're now at video 18, you'll see after I run this cell that we're actually taking some of what we've learned in earlier classes, including how to draw boxes on top of imagery in order to render the following output. And it was pretty fast. You'll see that in this face Haar cascade, in this grayscaled image of myself, you'll see that it only took about 262 milliseconds to run this entire cell. So again, there's nothing super fancy going on here, but fundamental computer vision algorithms. And again, the Haar cascade is relatively old. I mean, it's over at least 10 years old. It was able to run in literally under a second. So now we're going to jump over to another element. We're going to now take a quick look at TensorFlow and SSD MobileNet v2. So first, let me tell you a little bit about TensorFlow's Object Detection API, which is a powerful tool for detecting objects and images. One of the key things that you want to understand is that there is a model known as SSD MobileNet v2 Coco from TensorFlow. Imagine a tool that could essentially swiftly identify objects in an image, from a coffee mug on your desk to a zebra in the wild. At its core, the SSD MobileNet v2 Coco model combines 2 powerful concepts, SSD and MobileNet v2. SSD is basically shorthand for the single-shot multi-box detector, and it actually detects objects in a single forward pass of the network. Unlike other methods that have separate stages for generating region proposals and classifying them, SSD does it all at once, making it relatively fast and efficient. MobileNet v2, on the other hand, is a neural network architecture that's optimized for mobile and embedded devices, so it's meant to be lightweight yet powerful. By using inverted residuals and a linear bottleneck, as you'll see in this graphic that we're putting up, it's more efficient without compromising most accuracy. Finally, in the name of this model that we're going to import, the COCO and SSD MobileNet v2 signifies that the model is trained on the COCO dataset, which is a large-scale dataset for object detection, segmentation, and captioning. So why would you use SSD MobileNet v2 COCO? Well, it's kind of that sweet spot between speed and accuracy, and it makes it perfect for real-time object detection, especially on devices with limited computational power. Whether you're building a mobile app, flying a drone, or programming a robot, this model could be a game changer for you. So now below, I'm going to actually show you some code that we use to run an experiment with this. So first we'll have a regular preamble where we import TensorFlow and TensorFlow Hub. And then what we do is we actually import the underlying label map for SSD MobileNet v2, which is occurring right here in this line here. So I save it as the label map variable. This will be mostly useful because the outputs of these models typically will just output label 1, 2, 3, 4, 5. The label map just then allows you to bind that and say, oh, hey, actually label 1 is a cow, or label 17 could be some form of cat or bear or zebra. So now this is where the sort of the chunk of this code lies. We're going to time it like we did with the other, and you'll see we pulled in TensorFlow Hub in order for us to actually pull in this pre-trained model. So I'm not training a model from scratch, I'm literally just running it out of the box. All of this here is just loading and pre-processing the image, and you'll see that we're using TensorFlow input-output to read the file of Star Bunny, our favorite mascot, and what's on my shirt. We'll then convert that into an input tensor that can be accepted into the TensorFlow framework, and that's why we call model and pass as input the input tensor. You'll then see that we load it into NumPy array, and then this function is actually just diving deeply into how we can loop through each detection to draw a box over it. So I time all of this, and we will basically run and perform object detections by outputting those detections and then drawing those boxes in this function that I wrote here, known as draw boxes, onto the image. So without further ado, I will run this image. And you'll see that ran pretty fast. It took us, it looks like 6.82 seconds. And you'll see that, of course, it's not perfect. It's actually drawing a box, and it thinks that this Star Bunny is a bear. Of course, now you have to realize that we were just running the model out of the box. So it did indeed detect the object, but for whatever reason, some of the features that are associated with in the SSD MobileNet v2 COCO model tend to, I guess, have drawn connections and observed underlying features that are more akin to that of a bear. I'm not sure off the top of my head whether or not this model actually has a rabbit as a possible class. But you'll see here that it also rendered a score of 0.21, guessing that this image was actually that of a bear. So they're kind of mammals, right? I mean, they're close, but it's not perfect. Now we're going to jump into our third and different framework. This time we're going to use PyTorch, which has become more popular. And we're going to try a different model. We're going to use the faster RCNN. So diving into PyTorch, it's another deep learning framework that also offers robust tools for object detection. And here we're actually going to discuss a different architecture available from the Torch Vision library, which is why we import this. But we're going to actually pull in, it differs from what we just discussed with TensorFlow. So instead, I want you to imagine that you have a digital eye that not only sees objects, but also understands what they are. So that's the magic of actually having a faster RCNN, or faster recurrent convolutional neural network. And it's also underscored with ResNet 50 FPN. This comes from Torch Vision, but first let's break down that architecture and take a look at this graphic that we put up for you. So at its heart, the model uses faster RCNN, which stands for Faster Region-Based Convolutional Neural Network. It was one of the cutting-edge techniques for object detection, and it innovates by introducing a region proposal network, or RPN. Instead of relying on external tools for proposing regions where objects could be, the RPN actually does that automatically, making object detection literally faster. Likewise, the ResNet 50 in the name refers to the ResNet 50 backbone. ResNet, which stands short for residual network introduces the concept of skip connections or shortcuts. And it does these skip connections or shortcuts to actually avoid the vanishing gradient problem in deep networks. We'll dive into that in the intermediate class, but for now I want you to know that fact. And with 50 layers, this is actually deep enough for accurate performance and yet efficiency in real-world application. And again, as I mentioned with FPN, you might be wondering, what does that stand for? FPN stands for the Feature Pyramid Network. So traditional object detection often struggles with objects of varying sizes, but the Feature Pyramid Network, or FPN, addresses this by creating a multi-scale pyramid of features, ensuring that our model detects both the large elephant and the tiny ant in an image. So you would often choose faster RCNN or Resonant 50 FPN because it's a harmonious blend of speed, accuracy, and scalability. While other tools might excel in one area, this model strikes a sort of nice starting balance, making it a top choice for diverse object detection tasks in the world of computer vision. Essentially, it's a tool that you could use to truly see the bigger picture. So let's just jump right into this. I'm going to import my preamble of import statements. You'll see that we're pulling in Torch Vision and PyTorch. You can ignore this sort of warning. It's just basically saying that that iProgress loader was not found. And here's the magic of it. So you'll see that there's a similar structure to syntax, but it's a different library. Again, we're pulling in Torch Vision. I'm basically invoking faster RCNN ResNet, which comes from the Torch Vision models library. And then I run inference by calling model eval. After that's done, I actually will then actually load my image of the star bunny. So again, same image. And then what we do is we'll actually just perform object detection. I run with torch.no_grad to basically say, hey, I'm going to simply run prediction and pass that image that I loaded here after pre-processing to my model, which occurs with model.eval. I then want to extract all of my predictions, and I want to be able to see those different boxes, labels, and scores. You'll notice that there will actually potentially be more than one output, and this will be interesting for a variety of reasons, but let's just jump right into it. So when I run this script, you'll notice that it was incredibly fast, and we already had actually 4 different classes. And so performance here was much faster. The wall time was only 1.9 seconds. Interestingly, we also detected 4 objects with that model. Depending on the output, it either scored at the highest level, a bird, which is 0.87, the bear, similar to our other model in TensorFlow, which was 0.32 in this case. It also identified sports, which is a little confusing, and apple, which is 0.07. So all in all, this is telling us that, yeah, computer vision is not perfect. And again, we're just running this out of the box. However, were both models able to actually detect objects? Yes. Also, is there a trade-off between scale, performance, and speed? Also, yes. While this isn't perfect, this tells us that similarly to how a model is able to identify underlying patterns, we have to realize that a picture is worth 1,000 words. And with those words, we actually are trying to parse it using these computer vision algorithms to better understand what is happening under the hood. Essentially, object detection is pivotal in computer vision. And now in this example, you've seen how we can do this with hard cascades, with TensorFlow and with PyTorch, and we even explored 2 different models on our famous star bunny. This is video 18 out of 20 in our beginner series and introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Thanks so much for watching all, and I hope you have a great day. Hey, future visionaries. Are you ready to track objects like a pro using PyTorch and TensorFlow? In the next 15 or less minutes, we're going to dive deep into the world of computer vision It's going to be a wild ride, so buckle up and let's get started. This is video 19 out of 20 in our beginner series, an introduction to AI. By the end of the series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. All right, so first things first, what exactly is object tracking? Well, it's sort of like playing hide and seek with pixels. We follow objects as they move in video frames. Now let's see how we can be the Sherlock Holmes of our digital world. So first, let's set up our detective toolkit. You'll need, as you can see below, the CV2 library, Torch, Numpy, and Matplotlib, as well as a few other libraries. So follow along as I install them. Now, to give you some context, you'll actually observe that import torch actually imports the Python library. And you'll also see that the section here from torchvision.models.detection import faster RCNN ResNet 50 FPN is actually importing the faster RCNN model with a ResNet 50 backbone from TorchVision's model zoo. Likewise, by setting that model in this next section here to pre-trained equal to true, the value of doing so is that it sets the model into a state where we're using the model that has just been simply trained or pre-trained on a standard data set. Likewise, model.eval sets the model to evaluation mode. That step is necessary because this means that we disable layers like dropout and batch normalization, which will behave differently during training. You'll also notice that there's a copious amount of information that gets output when you run this cell. And that specifically walks through the underlying architecture of the imported neural network. Outputs like OpenCV1 or, as you can see, BN indicate what the subsequent layer is doing. For example, conv1 is a two-dimensional convolutional layer, and the output specifies both the kernel size, the stride, and the Boolean value associated with having bias. Likewise, BN1 indicates that a form of batch normalization was performed, and it also indicates that this layer is expecting an input of, in this case, 512 channels or features. We'll dive into these details in my intermediate class, which you can find online. But now that you've executed this cell, let's move on to the next section. Here, we simply store our .mov or .mp4 file to the video path. Make sure that you have the desired .mov or .mp4 in the same directory as a cell block. This cell just stores your video in the video variable on the second line. Okay, so to just sort of prepare you, although it's going to output nothing, to give you a little bit of the about, this basically renders the video for use in the following cell. To give you context, this was a video that I took at one of my friend's weddings the morning after the ceremony. So we were in NorCal near Carmel Beach, and I saw this swarm of birds flying, and I just thought this was so beautiful. So I'm going to run this cell, and a little anticlimactic, you don't see anything just yet because we're going to do one more step. And if you go back to our other videos, you'll remember that we imported things known as label maps. Think of it like this. Every detective needs their trusty toolkit. And here we actually have our label map, which is like a secret decoder ring that translates numbers into objects like cat or dog or mysterious shadow. And our main clue, the video file, is cunningly named here. And so, since we named that video path, we're going to simply import our Cocoa labels, and then this is where the meat of our function actually runs. So before we jump through it, let me actually explain the code, so that way this makes sense and you're not just blindly running a cell. So the first element that you really want to consider here is that, again, I traditionally love to sort of just put this magic time line so that way you can see how long it takes for the model to run in the way that you compose your code. When you go down here, this section is simply calculating the frame rates and setting up that frame limit. So you'll notice here that I basically set it up for 5 seconds worth of frames. I then initialize the frame count, we start at 0. And then we begin to peek into each frame of our movie and we hunt for objects. That gets instantiated when we begin this while video.isOpened and frame_count is less than the frame limit. In other words, the way to think about this is like you're looking through a flip book, but instead of having stick figures, we're looking at real life video feeds. And so what you're essentially doing is you're going frame by frame. As you can see here, we even iterate with frame plus equal to 1. And what we do is we execute this entire algorithm here. And what is actually happening? Well, I sort of commented it out for clarity, where first we're actually converting the color space from BGR to RGB, which we described why you do that in earlier videos. And then we actually converted the frame into an underlying tensor and save it to the frame tensor variable. Then this is actually where we use the stored model, and then we actually pass as input these frame tensors. So this is where the magic happens, where removing, again, the gradient descent element using with torch.nograd, we then execute the algorithm, and then we finally end up here by producing predictions. After you create predictions, you can then extract those underlying outputs, because in the predictions tensor, there will actually be boxes, labels, and scores that accompany each one of these elements. Think of it like this. In a high-tech lab, we transform each frame into a tensor, a fancy word for a multidimensional array. And sort of like flattening a Rubik's Cube, this lets us model our underlying data, and it allows you to peer into the data and make predictions with your all-seeing eye. And finally, this bottom part here is probably not the most exciting, but this is actually where the magic is happening. So basically what's happening is we're drawing these green boxes around our detected objects, which you'll see when I articulate, CV.rectangle. And what's going on is that they're not just any box. They're actually bounding boxes that will snugly fit around our objects of interest. We also include another line where we wanted to superimpose that text here to make it more simple for understanding the raw video feed. For a smoother viewing experience of the video with detections, I actually silenced the print label text render. However, if you want to actually see the type of object detected and the associated confidence score of the object, then you quickly stop this cell, uncomment the line, and then you'll see the actual raw numbers. So without further ado, I'm going to actually run this command, and you'll start seeing this underlying video. And I'm going to zoom in to make it a little bit easier. And you'll actually see that while the model is not perfect, it is per frame picking up different types of birds that I actually saw off the coast of Carmel. And as you can again imagine, because this is kind of a lower quality video and we're looking at it inside the context of Jupyter Notebook, you can't really see exactly what the model's text is saying, but you can see that it's churning ahead just fine. So now I'm going to perform what I just suggested, which is I'm going to actually interrupt this kernel. Don't worry here. This is purely for the learning experience. And then we're going to uncomment the print label text. And then what's going to happen now is you'll see actually all these outputs. And you'll observe that while it's not picking up all of the birds, it is roughly detecting the birds about with a confidence score of at least 0.8 for most of these objects, some of them even hitting 0.97. So it's relatively sure it's a bird. And again, you can see that it varies per output. So I'm going to pause this now. I don't like that jumpiness because it's refreshing and re-rendering the whole cell every time. But in general, you can imagine how a user can actually easily operationalize these detections by storing them historically into a repository. From there, you could actually even then get a pattern of life and observe trends in activity produced by the output of these object detections. You'll also notice that I ran a few filters here, so you were only seeing the most confident objects because I actually implemented a threshold here of 0.8. So if we change that, then the behavior will also likely alter. And you'll notice that again here, I only drew boxes, labels, and scores for those high confidence boxes. So feel free to play with this code at your leisure. And for this grand finale, I want you to know that you successfully exhibited frames in this grand museum of our Jupyter Notebook. Each frame is sort of like a work of art, and it displays all of our bounding boxes in their glory. When the code chain completes, we then release the video. And thus concludes our fantastical journey through code, where each line weaves a story of mystery, discovery, and even a little bit of playful mischief. Remember that in the world of object tracking, every pixel tells a tale. This is video 19 out of 20 and a beginner's series in Introduction to AI. By the end of this series, you'll be ready to learn more advanced concepts of AI and machine learning, which will allow you to elevate your career in tech and remain in demand on the job market. Hi everyone. Congratulations on watching through all 20 videos in this sequence. This is video 20 out of 20 in our beginner series on Introduction to AI. Coming out of this class, you should now know the basic fundamentals of AI, including its applications, how AI works, and the underlying history of AI as a field. We then spent 5 video lessons walking through some of the core Python fundamentals that walk you through how to set up your own local Python and Jupyter notebook environments. We also walked through topics like file handling, data structures, and Python basics, including functions and modules. You then learned how to use some of the underlying Python libraries that are the backbone for many AI-related applications, including Numpy, Pandas, and OpenCV. For each of these libraries, you also followed along to learn how we read, display, and save images, as well as how we perform common data operations and manipulations, including imputation and handling missing data. The last 6 videos then dove into a comprehensive introduction for computer vision. We went through the basics of image processing and image manipulation with OpenCV. We then went through filters and transforms available to you in OpenCV, as well as TensorFlow and PyTorch. You then dove into feature detection and matching. We then moved into both object detections, the use of hard cascades, performing facial detections, and even object tracking. As I mentioned, you are well on your way to becoming incredibly employable and understanding the foundational skills needed for computer vision. But this is only the beginning. If you're interested in learning more deeply about both generative AI and you want to learn some practical skills to build your own LLMs, fine-tune existing open source language and vision models, then check out my 8-week intermediate level course on generative AI that will equip you with the skills that you need to contribute to your own projects or organization as an AI engineer today. This is Batir, and if you found my beginners class sequence helpful, then definitely subscribe to my channel and leave your feedback about any new topics and specific skills that you'd like to learn. All the underlying code is also available through the GitHub link attached in each video. I hope to see some of you in my intermediate class for generative AI. To sign up, please feel free to just jump on over to my webpage and go from there. If you have any more questions, feel free to email me at this address below. Hope to see you soon.